Right now, at this very moment, something extraordinary is happening in space. Andromeda Galaxy, a massive collection of 1 trillion stars, is racing toward us at 250,000 miles per hour. That's fast enough to circle the Earth 10 times in a single hour. At that speed, you could travel from New York to Los Angeles in about 45 seconds. It's almost incomprehensibly fast by human standards. And yet, despite this incredible velocity, Andromeda won't reach us for approximately 4.5 billion years. Let that sink in for a moment. We're talking about an object moving at 250,000 miles per hour, and it still has 4.5 billion years of travel time ahead of it. This tells you something profound about the scale of space. The distances involved are so vast that even at these enormous speeds, cosmic events unfold over timescales that dwarf human history, dwarf the entire existence of our species, dwarf even the age of complex life on Earth. To put this in perspective, 4.5 billion years ago, Earth itself was just forming. The planet was a molten ball of rock, constantly bombarded by asteroids and comets. There was no life, no oceans, no atmosphere as we know it. Everything that's happened since then, the emergence of the first cells, the evolution of complex life, the rise and fall of the dinosaurs, the entire history of mammals, the brief flicker of human civilization, all of it has taken less time than we have until Andromeda arrives. So how do astronomers know this collision is coming? How can they predict an event billions of years in the future with any confidence? The answer lies in two powerful techniques: redshift measurements and proper motion studies. Let's start with redshift. When astronomers look at distant objects in space, they're not just seeing them, they're analyzing their light. Light carries information, and one of the most important pieces of information it carries is motion. This is because of something called the Doppler effect, the same phenomenon that makes an ambulance siren sound different as it approaches and then passes you. When a source of sound moves toward you, the sound waves get compressed, creating a higher pitch. When it moves away, the waves get stretched out, creating a lower pitch. Light does exactly the same thing. When an object in space moves toward us, its light waves get compressed toward the blue end of the spectrum. We call this blue shift. When an object moves away from us, its light gets stretched toward the red end of the spectrum. That's redshift. In 1912, an astronomer named Vesto Slipher was studying Andromeda, though at the time nobody knew for certain what Andromeda actually was. When he analyzed its light, he found something unusual. The spectral lines, which are like fingerprints in the light that tell us what elements are present, were shifted toward the blue end of the spectrum. Andromeda was blue shifted, meaning it was moving toward us, not away from us. This was actually surprising because most galaxies, as we later discovered, are moving away from us due to the expansion of the universe. But Andromeda is close enough that its gravitational attraction to the Milky Way overpowers the expansion of space. So instead of receding, it's approaching. By measuring exactly how much the light is blue shifted, astronomers can calculate the speed. The amount of shift tells you the velocity, and the answer they get is about 110 kilometers per second, or roughly 250,000 miles per hour. That's Andromeda's speed directly toward us along our line of sight. But there's another component to the motion. Andromeda isn't just moving straight toward us like an arrow. It's also moving slightly sideways, perpendicular to our line of sight. This sideways motion is called proper motion, and it's much harder to measure because it requires watching the galaxy's position change over many years. This is where the Hubble Space Telescope came in. Starting in the early 2000s, astronomers used Hubble to make extremely precise measurements of individual stars in Andromeda. By tracking these stars over several years, they could detect Andromeda's sideways motion across the sky. The motion is incredibly tiny, just fractions of an arcsecond per year. An arcsecond is 1/3600th of a degree, so we're talking about angular movements so small they're barely detectable even with our best instruments. But those measurements were enough. By combining the radial velocity from the blue shift with the sideways velocity from proper motion, astronomers could calculate Andromeda's full three-dimensional trajectory through space. And when they ran the calculations forward, accounting for the gravitational pull between the two galaxies, the answer was clear. Collision is inevitable. The exact timing has some uncertainty. Different studies have given estimates ranging from about 3.5 billion years to 5 billion years, with 4 to 4.5 billion years being the most commonly cited figure. The uncertainty comes from several factors. We don't know the exact mass of either galaxy with perfect precision. We don't know the exact distribution of dark matter in their halos, and there are smaller galaxies in the local group that might have minor gravitational effects on the trajectory. But all the studies agree on the fundamental conclusion. Andromeda is coming, and there's no way to avoid it. The gravitational pull between the two galaxies is too strong. We're locked into this cosmic dance, and it will end with the two galaxies merging into one. Now, when we say the collision will happen in 4.5 billion years, we need to be clear about what we mean by collision. This isn't like two cars crashing. Galaxies are mostly empty space. The stars are so far apart that when the galaxies interpenetrate, individual stellar collisions are essentially impossible. What we're really talking about is a gravitational interaction that will unfold over billions of years, involving multiple passages, tidal disruption, and eventually a complete merger. The cosmic clock is ticking, but it's ticking on a timescale so long that the word clock almost seems inappropriate. It's more like a geological process, or better yet, an evolutionary process. It happens so slowly that no single observer could ever watch it unfold in real time, and yet it's as inevitable as sunrise, written into the fabric of space-time by the laws of gravity. Before we can understand what's going to happen when these two galaxies collide, we need to understand what exactly is going to collide. So let's take a detailed look at both the Milky Way and Andromeda, compare their vital statistics, and see what makes each of them the cosmic titans they are. Start with our home galaxy, the Milky Way. It's what astronomers classify as a barred spiral galaxy. Picture a flat disk with graceful spiral arms curving outward from the center, kind of like a cosmic pinwheel. But unlike a simple spiral, the Milky Way has a bar-shaped structure at its core, a dense concentration of stars that extends out from the very center before the spiral arms begin. The Milky Way measures roughly 100,000 light-years, from edge to edge. To be clear about what that means, if you could somehow travel at the speed of light, it would take you 100,000 years just to cross from one side of our galaxy to the other. And remember, nothing can actually travel faster than light, so that's the absolute minimum time. In practical terms, with any realistic propulsion system, crossing the galaxy would take millions or tens of millions of years. As for how many stars the Milky Way contains, that's surprisingly hard to pin down. Estimates range from about 100 billion to 400 billion stars. That's a huge range, and you might wonder why we can't just count them. The problem is that we're inside the galaxy, embedded in its disk. When you look outward from Earth, your view is blocked by dust, gas, and the sheer density of nearby stars. It's like trying to count all the trees in a forest while you're standing in the middle of it. You can see some trees clearly, but your view of distant trees is blocked by the ones closer to you. The stars in the Milky Way aren't distributed evenly. They're concentrated in several structures. At the very center is the galactic bulge, a dense spherical region packed with old reddish stars. Within that bulge, at the exact center of the galaxy, sits a supermassive black hole called Sagittarius A, weighing about 4 million times what our sun weighs. We can't see the black hole directly, but we can see stars orbiting around it at incredible speeds, and by tracking those orbits, we can calculate the mass of whatever's at the center. Then there's the disk, where most of the galaxy's stars reside, including our sun. The disk is where you find the spiral arms, those graceful curves that give spiral galaxies their distinctive appearance. The spiral arms aren't permanent structures with fixed stars. They're more like traffic jams, regions where stars and gas are temporarily more concentrated as they orbit around the galactic center. Our Sun sits about 26,000 light-years from the galactic center, roughly halfway out to the edge. We're located in what's called the Orion Spur, a minor arm between two of the major spiral arms. And we're moving, orbiting around the galactic center at about 220 kilometers per second. Even at that speed, it takes us approximately 225 million years to complete one full orbit. The last time the Sun was in this exact position, dinosaurs were just beginning to dominate Earth. The Milky Way also has a halo, a roughly spherical region extending far beyond the visible disk. The halo is sparsely populated with old stars and globular clusters, which are tight balls of hundreds of thousands of ancient stars. The halo is also where most of the galaxy's dark matter resides, though we'll talk more about that later. Now let's look at Andromeda, also known as M31. It's similar to the Milky Way in many ways, also a barred spiral galaxy, but it's noticeably larger. Andromeda measures about 220,000 light-years across, more than twice the diameter of the Milky Way. That means it has about 4 times the disk area, giving it significantly more room for stars. And indeed, Andromeda has more stars. Current estimates put its stellar population at around 1 trillion stars, at least 2 to 3 times more than the Milky Way, possibly more. That's a staggering number. If you tried to count to 1 trillion, counting one number per second without stopping, it would take you about 32,000 years. Andromeda's supermassive black hole is much larger than ours. While Sagittarius A weighs 4 million solar masses, Andromeda's central black hole weighs somewhere between 100 million and 200 million solar masses. That's at least 25 times heavier, possibly 50 times heavier. This difference will matter when the galaxies merge and the black holes eventually combine. Both galaxies have satellite galaxies, smaller galaxies that orbit around them like moons orbiting a planet. The Milky Way has dozens of satellite galaxies. The most famous are the Large and Small Magellanic Clouds, which are visible from the southern hemisphere as fuzzy patches in the night sky. There's also the Sagittarius Dwarf Elliptical Galaxy, which is currently being torn apart by the Milky Way's gravity, its stars scattered in long streams that wrap around our galaxy. Andromeda has its own collection of satellites, at least 14 confirmed dwarf galaxies orbiting around it. The most notable is M32, a compact elliptical galaxy that sits very close to Andromeda's core. There's also M110, another dwarf elliptical that's been partially disrupted by tidal forces from Andromeda. Together, the Milky Way and Andromeda dominate what astronomers call the local group. This is our neighborhood cluster, containing roughly 80 known galaxies spread across about 10 million light-years. But of those 80 galaxies, most are tiny dwarf galaxies containing just a few million or billion stars. The Milky Way and Andromeda are the giants, containing the vast majority of the local group's total mass. The third largest galaxy in the local group is the Triangulum Galaxy, also known as M33. It's a spiral galaxy containing perhaps 40 billion stars, making it substantial but still much smaller than either the Milky Way or Andromeda. Triangulum is actually gravitationally bound to Andromeda, orbiting around it at a distance, and it will likely be pulled into the collision as well. The combined mass of the Milky Way and Andromeda, including their dark matter halos, is roughly 2 to 3 trillion times the mass of the Sun. That's the total mass involved in this collision, and that mass creates a gravitational field that influences everything in the local group. The smaller galaxies, the intergalactic gas, even the paths of light passing through the region, all of it is affected by the gravity of these two titans. When we talk about these galaxies dominating the local group gravitationally, here's what that means practically. Any smaller galaxy that wanders too close to either the Milky Way or Andromeda gets captured. Its orbit becomes bound to the larger galaxy. Over time, tidal forces stretch and distort it. Eventually, it gets completely torn apart, its stars absorbed into the larger galaxy. This has happened many times in the past, and it's happening right now with several satellite galaxies. In fact, both the Milky Way and Andromeda have been built up over billions of years through this process of absorbing smaller galaxies. When astronomers study the distribution of stars in both galaxies carefully, they can see evidence of past mergers. There are streams and shells of stars, remnants of dwarf galaxies that were consumed long ago. The history of both galaxies is written in the positions and velocities of their stars, if you know how to read it. So that's what we're dealing with. Two massive spiral galaxies, each containing hundreds of billions of stars, each surrounded by dozens of smaller satellite galaxies, each embedded in a massive halo of dark matter. They're the two dominant structures in our corner of the universe, and they're on a collision course. For most of human history, we had no idea Andromeda was even a galaxy, let alone that it was approaching us. The story of how we discovered our cosmic destiny is a fascinating journey through the history of astronomy, involving generations of observers, each one adding a piece to the puzzle. Andromeda has been visible to humans for as long as humans have had eyes. It's one of the most distant objects you can see without a telescope, a faint fuzzy smudge in the constellation Andromeda. Ancient astronomers noticed it. The Persian astronomer Abd al-Rahman al-Sufi described it back in the year 964, calling it a small cloud, but nobody understood what they were looking at. For centuries, astronomers assumed Andromeda was a nebula, a cloud of gas somewhere within our own galaxy. The idea that there might be other galaxies beyond our own, that the universe might contain countless separate island universes, that was too radical to even consider seriously. The first hint that something unusual was happening came in 1912. An American astronomer named Vesto Slipher was working at Lowell Observatory in Arizona, studying the spectra of various nebulae. When you pass light through a prism or a spectrograph, it spreads out into its component colors, creating a spectrum. Within that spectrum, you see dark lines at specific wavelengths, absorption lines created when certain elements in the object absorb light at characteristic frequencies. These spectral lines are like fingerprints. Each element creates its own unique pattern. If you see the pattern for hydrogen, you know hydrogen is present. If you see the pattern for calcium, you know there's calcium. But here's the key insight. If the object is moving relative to you, those spectral lines shift. If the object is moving toward you, all the lines shift toward the blue end of the spectrum. If it's moving away, they shift toward red. When Slipher examined Andromeda's spectrum, he found something remarkable. The spectral lines were blue shifted toward shorter wavelengths. This meant Andromeda was moving toward us. He calculated the velocity at about 300 kilometers per second, though later, more precise measurements revised this to about 110 kilometers per second or 250,000 miles per hour. This was surprising because Slipher had measured several other nebulae, and most of them showed redshifts, indicating they were moving away from us. Andromeda was unusual in approaching us, but at the time, nobody really understood what this meant because nobody knew what Andromeda actually was. The breakthrough came in the 1920s with Edwin Hubble. Hubble was working with the 100-inch Hooker telescope at Mount Wilson Observatory in California, then the largest telescope in the world. He was studying Andromeda in unprecedented detail, and he discovered something extraordinary. Within Andromeda, Hubble identified individual stars. Not just any stars, but a specific type of variable star called Cepheid variables. These stars are incredibly useful for measuring distances because they pulsate with a regular period, and that period is directly related to their intrinsic brightness. If you know how bright a Cepheid really is, and you measure how bright it appears from Earth, you can calculate its distance using the inverse square law. When Hubble measured the Cepheids in Andromeda and calculated the distance, He got a result of roughly 900,000 light-years. We now know the actual distance is about 2.5 million light-years, so Hubble's initial estimate was too low, but even his underestimate was enough to prove that Andromeda was far outside the Milky Way. It couldn't possibly be a nebula within our galaxy. It had to be a separate galaxy altogether. Hubble announced this discovery in 1925, and it revolutionized our understanding of the universe. Suddenly, the cosmos was vastly larger than anyone had imagined. The Milky Way wasn't the entire universe. It was just one galaxy among countless others scattered throughout an incomprehensibly large space. But knowing that Andromeda was approaching us, and knowing it was a separate galaxy, still didn't tell us the full story. The question was, would it actually hit us, or would it pass by? And if it was going to hit, when? To answer these questions, astronomers needed more precise measurements. They needed to know not just Andromeda's speed toward us, but also its sideways motion across the sky. This is where things got challenging, because that sideways motion, the proper motion, is incredibly tiny. Think about it this way. Andromeda is 2.5 million light-years away. Even though it's moving at 250,000 miles per hour, from our perspective, that translates into an angular motion of only about 0.001 arcseconds per year. An arcsecond is 1/3600th of a degree, so we're talking about an angular change of 1,000th of that per year. It's extraordinarily difficult to measure. For decades, astronomers tried to measure Andromeda's proper motion, but the results were inconclusive. The measurements weren't precise enough to say for certain whether we were on a collision course. There was genuine uncertainty about our fate. The breakthrough came in the 2000s with the Hubble Space Telescope. Hubble, orbiting above Earth's atmosphere, could make incredibly sharp images free from the blurring effects of atmospheric turbulence. Astronomers used Hubble to photograph specific regions of Andromeda, measuring the positions of individual stars with extraordinary precision. Then they waited. They came back several years later and photographed the same regions again. By comparing the two sets of images, they could detect tiny shifts in the positions of stars, shifts caused by Andromeda's motion across the sky. The observations were led by astronomers Roland van der Merel and Sangmo Tony Sohn, and they published their results in 2012, exactly 100 years after Slipher's original discovery. Their conclusion was definitive. Andromeda is on a collision course with the Milky Way. The collision will begin in approximately 4 billion years. They could also predict the nature of the collision. Because they now knew Andromeda's full three-dimensional velocity, they could run computer simulations forward in time, modeling how the two galaxies would interact. The simulations showed that the galaxies wouldn't just collide once, they would pass through each other, swing back around due to their mutual gravity, and collide again. This process would repeat multiple times over the course of about 2 billion years before the galaxies finally settled into a single merged galaxy. Later observations refined these predictions. In 2019, more detailed proper motion measurements were published, using additional years of Hubble data. These confirmed the earlier results and slightly refined the timeline and trajectory. The collision is definitely coming, and we now understand it in considerable detail. The discovery of our cosmic destiny is a perfect example of how science works. It started with a single observation in 1912, an unexpected blue shift. That observation raised a question. What does this mean? Over the following decades, astronomers gradually assembled more pieces of the puzzle. They figured out that Andromeda was a separate galaxy. They measured its distance more accurately. They developed the theoretical framework to understand galaxy dynamics. They built better telescopes and refined their measurement techniques. Each generation of astronomers built on the work of the previous generation, and eventually, after a century of effort, we arrived at a clear answer. We know where Andromeda is. We know where it's going. And we know that in 4 billion years, the Milky Way and Andromeda will collide, merge, and become something new. It's a testament to human ingenuity and persistence. We've taken a faint smudge in the night sky and figured out not just what it is, but where it's headed and what will happen when it gets here. We've predicted the future of our galaxy billions of years in advance, using nothing but light, mathematics, and careful observation. Gravity is the force that will bring the Milky Way and Andromeda together. So before we go any further, we need to understand how gravity works, especially over the enormous distances we're dealing with. Because here's something fascinating. The gravitational dance between our two galaxies has already begun. Right now, at this very moment, the Milky Way and Andromeda are pulling on each other, even though they're 2.5 million light-years apart. Let's start with the basics. Gravity is one of the four fundamental forces of nature, and in many ways it's the simplest. Any object with mass attracts any other object with mass. The strength of that attraction depends on two things: how much mass the objects have and how far apart they are. The more massive the objects, the stronger the gravitational pull between them. The Earth pulls on you, and you pull on Earth. But Earth is vastly more massive than you, so its pull on you is much stronger than your pull on it. That's why you fall toward Earth instead of Earth falling toward you. Though technically Earth does move toward you, just by an amount so small it's completely unmeasurable. Distance matters too, and it matters a lot. Gravity follows what's called an inverse square law. If you double the distance between two objects, the gravitational force between them becomes 4 times weaker. Triple the distance, and the force becomes 9 times weaker. The force drops off rapidly as you increase the separation. This raises an interesting question. If gravity gets weaker with distance, and Andromeda is 2.5 million light-years away, how can it be pulling on us at all? Shouldn't the distance be so large that the gravitational force is negligible? Here's where the sheer mass of galaxies comes into play. The Milky Way contains somewhere between 200 and 400 billion stars, plus vast amounts of gas, dust, and dark matter. The total mass is roughly 1 trillion times the mass of the Sun. Andromeda is even more massive, perhaps 1.5 trillion solar masses. When you're dealing with masses this enormous, even at distances of millions of light-years, the gravitational pull is substantial. Think of it this way. Imagine you're trying to pull a car with a rope. If the rope is short, you can pull hard. If the rope is very long, the pull is weaker. But if instead of you pulling, you have 1,000 people pulling, even with a very long rope, the car is going to move. Andromeda and the Milky Way are like two groups of 1 trillion people each, all pulling on opposite ends of an extremely long rope. Right now, this gravitational pull is causing both galaxies to accelerate toward each other. They're not moving at constant speed. They're speeding up as they get closer, because the gravitational force increases as the distance decreases. 4 billion years from now, when they're much closer, they'll be moving even faster than the current 250,000 miles per hour. But gravity doesn't just pull the galaxies toward each other as whole units. It also creates tidal forces stretching and distorting each galaxy. To understand tidal forces, think about Earth and the Moon. The Moon pulls on Earth, but it doesn't pull on all parts of Earth equally. The side of Earth closest to the Moon feels a stronger pull than the center of Earth, which feels a stronger pull than the side farthest from the Moon. This difference in gravitational force across Earth's diameter is what creates tides in the oceans. The same thing happens with galaxies, but on a vastly larger scale. The parts of the Milky Way closest to Andromeda feel a stronger pull from Andromeda than the parts farthest away. This creates a stretching force, elongating the galaxy toward Andromeda, and it works both ways. The Milky Way's gravity stretches Andromeda too. These tidal forces are still relatively weak right now because the galaxies are so far apart, but they're there and they're growing. As the galaxies approach each other, the tidal forces will become stronger. Eventually, They'll be strong enough to visibly distort the spiral structure, pulling long tidal tails of stars out of both galaxies. Now let's talk about dark matter, because it plays a crucial role in all of this. When astronomers measure the mass of a galaxy by observing the motion of stars and gas, they find something puzzling. The visible matter, all the stars, gas, and dust, doesn't account for the total mass. There's additional mass present that we can't see, mass that doesn't emit, absorb, or reflect light. We call this dark matter, and it makes up roughly 85% of the matter in the universe. We don't know what dark matter is made of. The leading hypothesis is that it's some exotic particle that barely interacts with normal matter except through gravity. But whatever it is, we know it's there because of its gravitational effects. Every galaxy, including the Milky Way and Andromeda, is surrounded by a dark matter halo. This halo extends far beyond the visible disk of the galaxy. While the visible Milky Way is about 100,000 light-years across, its dark matter halo extends perhaps 300,000 light-years or more. For Andromeda, with its larger visible disk, the dark matter halo might extend 500,000 light-years or even farther. The dark matter halo contains several times more mass than all the visible matter in the galaxy. In fact, the dark matter provides most of the gravity that holds the galaxy together. Without it, galaxies would fly apart. The visible matter is rotating so fast that the gravity from the visible matter alone isn't enough to keep it bound. These dark matter halos are important for the collision because they reach out much farther than the visible galaxies. Right now, even though the visible parts of the Milky Way and Andromeda are 2.5 million light-years apart, their dark matter halos are already interacting. In fact, depending on exactly how large the halos are, they might already be overlapping. When the galaxies finally collide, the dark matter halos will merge first, long before the visible disks touch. And because dark matter makes up most of the mass, it's really the dark matter halos that drive the merger. The visible matter, the stars and gas, are just along for the ride, responding to the gravitational field created by the combined dark matter halos. Here's another way to think about it. The visible galaxy is like a fly caught in a spider's web. The web is the dark matter halo. When two webs come together, they tangle and merge, and the flies trapped in them get pulled together in the process. The dark matter webs are merging, and the visible galaxies have no choice but to follow. The gravitational interaction between the Milky Way and Andromeda is also affecting the smaller galaxies in the local group. Every galaxy is pulling on every other galaxy. The smaller dwarf galaxies, caught between the two giants, are feeling gravitational tugs from multiple directions. Some of them will eventually fall into one of the larger galaxies and be absorbed. Others might be flung out of the local group entirely, ejected by the complex gravitational interactions. The Triangulum Galaxy, the third largest member of the local group, is already gravitationally bound to Andromeda. It orbits around Andromeda at a distance of roughly 750,000 light-years. As Andromeda approaches the Milky Way, Triangulum will be dragged along. It might collide with Andromeda before the main Milky Way-Andromeda collision, or it might hit during the merger, adding its own mass to the chaos. One of the fascinating things about gravity is that it's completely deterministic. If you know the positions, velocities, and masses of all the objects involved, you can calculate exactly how they'll move in the future. This is how astronomers can predict the collision with such confidence. They've measured the positions and velocities. They've estimated the masses. They've run computer simulations that solve the equations of motion, and all the simulations give the same basic result. Collision is inevitable. Of course, there are uncertainties. We don't know the exact mass of either galaxy with perfect precision. We don't know the exact shape and extent of the dark matter halos. We don't know if there are significant amounts of matter in intergalactic space that might affect the trajectories. But these uncertainties only affect the details, the exact timing, the precise trajectory during the collision. They don't change the fundamental outcome. The gravitational dance has begun, and it will continue for the next 4 billion years, with both galaxies slowly falling toward each other, accelerating as they approach, until finally they meet in one of the most spectacular events the universe has to offer. Before we can appreciate how dramatically the night sky will change during the collision, we need to establish a baseline. What does Andromeda look like right now from Earth? For most people, even people who spend time looking at the night sky, Andromeda is barely noticeable, and that's about to make the future changes all the more striking. If you go outside tonight, assuming you're in the northern hemisphere and it's the right time of year, roughly autumn or early winter, you can see Andromeda with your naked eyes. But you need to be in a dark location, away from city lights. Light pollution from streetlights, buildings, and cars washes out faint objects in the sky, and Andromeda is definitely on the faint side. Find a truly dark site, let your eyes adjust for at least 20 minutes, and look toward the constellation Andromeda. What you'll see is a small, faint, fuzzy patch of light. That's it, nothing dramatic. Nothing that would make you stop and stare. Just a subtle smudge that you might mistake for a small cloud if you didn't know what you were looking at. That fuzzy patch is actually just the bright central core of Andromeda. The galaxy itself is much larger than what we can see with our naked eyes. If we could somehow see the entire extent of Andromeda, its full halo of stars and gas, it would appear about 6 times wider than the full moon in our sky. But most of those outer regions are too faint to see without long exposure photography. Through binoculars, Andromeda looks a bit better. The fuzzy patch becomes more defined. You can start to see that it's elongated, stretched out in a particular direction. This is because we're viewing Andromeda at an angle, not face-on. If you were to look at it from above, you'd see the full spiral structure, but from our perspective, it's tilted, giving it an elliptical appearance. With a small telescope, maybe 4 or 6 inches in aperture, you can start to pick out more structure. The central bulge becomes clearly defined, a brighter region at the heart of the galaxy. You might start to see hints of the spiral arms, though they're subtle. And if the seeing is good, meaning the atmosphere is steady, you might catch glimpses of dark dust lanes, regions where dense clouds of dust block the light from stars behind them. Larger telescopes reveal even more. With an 8-inch or 10-inch telescope, the spiral structure becomes more obvious. You can see multiple spiral arms winding out from the core. You can clearly see dust lanes threading through the galaxy. And you can spot some of the bright star-forming regions, areas where new stars are being born, glowing with the light of young, hot stars. If you take a photograph with a long exposure, the camera can capture details that the eye can't see. Modern astrophotography reveals Andromeda in stunning detail. The spiral arms become crisp and well-defined. The dust lanes stand out as dark ribbons against the background glow. Star-forming regions appear as bright knots of blue light, and the outer halo of the galaxy becomes visible, a faint glow extending well beyond the main disk. 2 of Andromeda's satellite galaxies are also visible in photographs, M32 and M110. M32 is a compact elliptical galaxy that sits very close to Andromeda's core. M110 is farther out, a dwarf elliptical that appears as a separate fuzzy patch. Both are gravitationally bound to Andromeda, orbiting around it, and both will be involved in the eventual collision. But even with all this detail revealed through telescopes and cameras, Andromeda is still just one object among many in our night sky. It's beautiful, certainly, especially in photographs. But it doesn't dominate. It doesn't draw the eye the way the moon does, or a bright planet like Venus or Jupiter. It's just one more celestial object, special to those who know what it is, but easily overlooked by casual observers. This is what makes the coming transformation so profound. Right now, Andromeda is barely visible, a faint smudge that most people never notice. In 4 billion years, it will fill the sky, an overwhelming presence that would be impossible to ignore. The change will be so dramatic that it's almost hard to imagine. The Milky Way itself is more prominent in our current night sky than Andromeda. If you're in a dark location and look up on a clear, moonless night, you can see the Milky Way as a broad, diffuse band of light stretching across the sky. This is our view of our own galaxy from inside. We're looking through the disk, seeing the combined light of billions of stars, too distant and faint to see individually. The Milky Way appears as a band because we're inside a disc-shaped galaxy. When you look toward the center of the galaxy, toward the constellation Sagittarius, the band is brightest and widest. When you look in other directions, perpendicular to the galactic disk, you see many fewer stars, and the Milky Way band fades. Unfortunately, many people have never seen the Milky Way. Light pollution has washed it out from most populated areas. If you live in or near a city, the sky is never truly dark. The glow from artificial light scatters through the atmosphere, creating a background brightness that obscures faint objects. To see the Milky Way properly, you need to travel to a genuinely dark site, far from cities and towns. But for those who have seen it, the Milky Way is one of the most beautiful sights in nature. It's humbling to look up and realize you're seeing your own galaxy, the island universe that contains our sun and earth, and everything we've ever known, laid out across the sky. This is the baseline then. Our current night sky, with Andromeda as a barely visible smudge, and the Milky Way as a diffuse band of light. Remember this view, because it's going to change in ways that are hard to fully comprehend. The faint smudge will grow into a galaxy that fills the heavens. The Milky Way band will be joined by another, then distorted, then eventually merged into something completely different. The sky our distant descendants will see, assuming they're around to see it, will bear no resemblance to the sky we know today. Now let's jump forward in time. Not all the way to the collision, but to a point about 1 billion years before contact. We're now 3.5 billion years in the future, and things are starting to change noticeably. Andromeda is getting larger in the night sky. It's still not huge, not yet dominating the heavens, but it's definitely more prominent than it was in our era. What used to be a faint smudge visible only under dark skies has grown into a more obvious feature. It's now easily visible even from moderately light-polluted areas, and from dark sites, it's striking. The galaxy now appears roughly twice as wide as the full moon, and it's continuing to grow. If you were to observe the sky over a human lifetime, say 80 or 90 years, you might just barely notice the change. Andromeda would be slightly larger at the end of your life than at the beginning. It's not dramatic on human timescales, but it's there. But here's what's interesting. If records have been kept, if there's some form of civilization maintaining observations over centuries or millennia, the trend would be unmistakable. Astronomers would have detailed measurements showing that Andromeda has been steadily growing larger, year after year, decade after decade, century after century. They'd be able to plot its growth and predict with great accuracy when the collision will occur. This would be a society living with the knowledge that a cosmic collision is coming, not in the distant, abstract future, but within a time frame that might feel relevant. 1 billion years is still enormously long by any human measure, but if you're a civilization with a long historical record, if you can look back and see how much things have changed over the last billion years, then 1 billion years into the future doesn't seem quite so remote. The psychological impact of this sight is worth considering. Imagine growing up under a sky where Andromeda is a prominent feature, visibly larger than anything else except the moon. Imagine being taught in school that this galaxy is approaching, that eventually it will collide with the Milky Way, and that the night sky your grandchildren's grandchildren's grandchildren see will be completely different from the sky you know. It would create a certain cosmic perspective. The universe would feel dynamic, alive, changing. You'd know viscerally that nothing is permanent, not even the galaxies themselves. This might foster a long-term way of thinking, an understanding that your actions have consequences that ripple forward through enormous spans of time. Or it might create anxiety. The collision, even though it's a billion years away, is inevitable. There's no way to stop it, no way to change course. You're living on a planet orbiting a star in a galaxy that's going to be completely transformed, and there's nothing anyone can do about it. How would a society cope with that knowledge? Let's think about what the night sky actually looks like at this point. Andromeda is larger and brighter, clearly visible as a galaxy, rather than just a vague smudge. Through telescopes, its structure is more apparent. The spiral arms are easier to see. Individual bright stars within Andromeda might be distinguishable, the most luminous supergiants standing out as distinct points of light. The Milky Way itself looks much as it always has, still that broad band of light crossing the sky. Our own galaxy hasn't changed much in visible appearance from the inside, though astronomers studying it carefully would notice some differences. Some older stars have died, new stars have formed. The spiral arms have shifted slightly as the galaxy continues its slow rotation. But the big change is Andromeda, growing slowly but steadily, an ominous reminder of what's to come. And it's not just getting bigger, it's also getting brighter. As it approaches, the inverse square law works in reverse. The brightness of an object increases as it gets closer, and Andromeda is now much closer than it was in our time. The increase in brightness makes it easier to study, easier to see with the naked eye, and more prominent in the overall appearance of the night sky. If there are amateur astronomers at this time, they'd be having a field day with Andromeda. With even modest telescopes, they'd be able to see details that we can barely glimpse with our best equipment. Individual star clusters within Andromeda would be resolvable. The dust lanes would be crisp and clear. The star-forming regions would glow vividly. Professional astronomers would be monitoring the approach carefully. They'd be measuring Andromeda's motion with extreme precision, tracking its trajectory, and looking for the first signs of gravitational interaction between the galaxies. And at this point, 1 billion years before impact, those signs would be starting to appear. Remember, gravity acts over distance. The galaxies don't have to be touching for their gravity to affect each other. At 1 billion years out, Andromeda and the Milky Way are perhaps 1 million light-years apart, maybe a bit less. That's close enough for their gravitational fields to start having measurable effects. The dark matter halos, extending far beyond the visible galaxies, are almost certainly overlapping by this point. Dark matter doesn't emit light, so we can't see this directly, but astronomers could infer it from careful studies of the motions of stars and gas in both galaxies. They'd see subtle deviations from the expected orbits, small perturbations caused by the gravitational influence of the approaching galaxy. The outer regions of both galaxies might show the first hints of tidal distortion. Stars on the side facing the other galaxy feel a slightly stronger pull than stars farther away, and this difference in force creates a stretching effect. It's not dramatic yet, but it's measurable. The galaxies are beginning to elongate slightly toward each other. Gas clouds in the outer parts of both galaxies might also be affected. Gas is less dense than stars and more easily disturbed by gravitational forces. Astronomers might detect streams of gas being pulled from one galaxy toward the other, the earliest precursors of the tidal tails that will become prominent later. All of this would be visible only through careful scientific study. To the naked eye, the sky would still look fairly normal, just with a larger Andromeda. But the data would tell a different story. The collision isn't just coming, it's already beginning in subtle ways. The gravitational dance that started 2.5 billion years ago, when the galaxies were much farther apart, is now entering a new phase, one where the effects are becoming noticeable. This is also a time when any advanced civilizations in either galaxy would be making plans. 1 billion years is enough time to do a lot. If space travel is possible, you could colonize vast numbers of star systems spreading across the galaxy to reduce the risk that any single event wipes you out. If megastructure engineering is possible, You could build habitats that are independent of planets, self-contained environments that can be moved if necessary. 1 billion years is also enough time for natural evolution to produce new forms of life, new adaptations to whatever environmental changes are occurring. If conditions on Earth or any other planet are becoming less hospitable due to the aging of their host stars, life might migrate to new worlds or adapt to survive in space itself. The point is, at 1 billion years before impact, the collision is no longer just a distant, abstract threat. It's real, it's measurable, and it's close enough that any sentient beings would be taking it seriously, planning for it, preparing in whatever ways their technology and capabilities allow. Before we get to the collision itself, we need to talk about what's happening to our own galaxy during these billions of years. The Milky Way isn't sitting still, frozen in time, waiting for Andromeda to arrive. It's evolving, changing, and by the time the collision begins, it will be quite different from the galaxy we know today. Let's start with the Sun, because the Sun's evolution has major implications for Earth and the inner solar system. Right now, the Sun is about 4.6 billion years old, roughly halfway through its main sequence lifetime. Main sequence is the term astronomers use for the stable phase of a star's life, when it's fusing hydrogen into helium in its core. The Sun has enough hydrogen fuel to continue this process for another 5 billion years or so. But here's something that's not widely appreciated. The Sun is getting brighter over time, even during its main sequence phase. This happens because as hydrogen fuses into helium, the core becomes denser with helium ash. This denser core fuses hydrogen slightly faster, producing more energy, which makes the Sun more luminous. The effect is gradual but significant. Over the Sun's lifetime, its luminosity increases by about 40%. By 4 billion years from now, when the collision begins, the Sun will be noticeably brighter and hotter than it is today. This has serious implications for Earth. The amount of solar energy hitting Earth will be significantly higher. The climate will be much warmer. Most models suggest that within 1 billion years, maybe 2 at most, Earth's oceans will begin to evaporate. The increased solar radiation will heat the surface, evaporating more water into the atmosphere. Water vapor is a greenhouse gas, so this creates a positive feedback loop. More evaporation leads to more warming, which leads to more evaporation. Eventually, the oceans will be gone entirely. Earth will become a hot, dry planet with a thick atmosphere of water vapor and carbon dioxide. Surface temperatures will soar, possibly reaching several hundred degrees. Any life still on the surface will be long dead. By 4 billion years from now, Earth is almost certainly uninhabitable. It might look something like Venus does today, a scorched world with a crushing atmosphere and surface conditions that would melt lead. This is the Sun's fault, not the collisions. This would happen even if Andromeda weren't approaching. The Sun itself will still be a main sequence star at this point, still fusing hydrogen, but it will be nearing the end of this stable phase. Within another 1 billion years or so after the collision, the Sun will exhaust the hydrogen in its core and begin its transformation into a red giant. But during the collision, it will still be recognizably the same type of star it is today, just brighter and older. Now let's think about the Milky Way as a whole. Over 4 billion years, billions of stars will be born, and billions will die. The galaxy is constantly forming new stars from its reservoirs of gas and dust. These new stars light up the spiral arms, creating the bright blue regions we see in spiral galaxies. But star formation isn't uniform throughout the galaxy. It happens primarily in the spiral arms and in regions where gas is compressed. The spiral arms aren't permanent structures. They're density waves, regions where stars and gas bunch up temporarily as they orbit around the galactic center. As stars move through a spiral arm, they slow down slightly, causing a traffic jam effect. This compression triggers star formation, which is why the arms appear bright. Over 4 billion years, the spiral structure will shift. The arms will be in different positions relative to where they are now. Stars will have moved. The Sun, completing roughly 18 orbits around the galactic center in that time, will have passed through spiral arms multiple times and will be in a different location than it is today. Some of the stars we see in our night sky today will be gone. High-mass stars, those weighing more than about 8 solar masses, have short lifetimes. The most massive stars live only a few million years before exploding as supernovas. Even medium-mass stars, those a few times the Sun's mass, will have completed their life cycles within 4 billion years. But new stars will have formed to replace them. The galaxy's total stellar population will be roughly the same, though the mix of stars will be different. There will be fewer high-mass stars and more low-mass stars, and stellar remnants, white dwarfs, neutron stars, and black holes. The spiral structure itself might look somewhat different. Spiral galaxies aren't static. Their spiral patterns can change over time due to gravitational interactions with other galaxies or due to internal processes. By the time Andromeda arrives, the Milky Way's spiral arms might be more tightly wound, or more loosely wound, or shifted in orientation. The supermassive black hole at the center of the galaxy, Sagittarius A, will still be there, possibly slightly larger from consuming gas and the occasional star, but it won't have changed dramatically. Supermassive black holes grow slowly, and 4 billion years isn't enough time for major growth unless something unusual happens. The satellite galaxies orbiting the Milky Way will have changed as well. Some, like the Sagittarius dwarf elliptical galaxy, which is currently being torn apart by the Milky Way's tides, will be completely absorbed by this point. Their stars will be scattered throughout the Milky Way, indistinguishable from the rest of the galaxy's population. Other satellite galaxies, like the Large and Small Magellanic Clouds, might still be separate entities, though they'll be closer to the Milky Way and showing more signs of tidal distortion. Eventually, these too will be absorbed, but the exact timing depends on their orbits and the details of how they interact with the Milky Way's gravitational field. The interstellar medium, the gas and dust between the stars, will have been enriched with heavy elements from billions of years of stellar evolution. Every massive star that explodes as a supernova adds elements like oxygen, carbon, iron, and silicon to the interstellar medium. This enriched gas gets incorporated into new stars and planets, making each successive generation of stars slightly more metal-rich than the last. By 4 billion years from now, the average metallicity of the galaxy will be noticeably higher than it is today. This matters for planet formation. Rocky planets are made from heavy elements, so a higher metallicity means more material available to build planets. Planetary systems forming at this time might have more rocky planets or larger rocky planets than systems forming today. So this is the Milky Way that will collide with Andromeda, a mature spiral galaxy. Still forming stars, but at a gradually declining rate, with a mixed population of stars ranging from ancient red dwarfs billions of years old to brand new massive stars just being born, embedded in a dark matter halo that extends far beyond the visible disk, orbited by a handful of small satellite galaxies and centered on a supermassive black hole. It's a galaxy that's lived a long life, that's absorbed many smaller galaxies over its history, that survived in the same general form for billions of years. And now it's about to be transformed completely, merged with another galaxy of comparable size, to create something entirely new. We're now much closer to the collision, just 500 million years away from first contact. This is when things start to get truly spectacular. The changes that were subtle 1 billion years ago are now obvious, undeniable, and increasingly dramatic. Andromeda dominates the night sky. It's no longer just a prominent feature, it's overwhelming. The galaxy now appears several times wider than the full moon, a massive structure that draws the eye immediately whenever you look up at night. But more than just its size, the detail is incredible. Andromeda's spiral structure is clearly visible to the naked eye. You can see the spiral arms curving outward from the bright central bulge. You can see regions of bright blue light, massive star-forming regions where thousands of new stars are being born. And threading through everything, you can see dark lanes of dust silhouetted against the background glow. This is something no human in our era has ever seen. A galaxy in such exquisite detail, visible without any optical aid. With telescopes today, we can see these features in distant galaxies, but only Andromeda and the Magellanic Clouds are close enough to show any structure to the naked eye, and even then, it's subtle. But 500 million years before contact, there's nothing subtle about it. Andromeda is a full-fledged galaxy sprawled across the heavens. For any civilization witnessing this, the psychological impact would be profound. This isn't an academic abstraction. This isn't something happening far away. This is immediate, visible, undeniable. The collision is coming, and you can see it with your own eyes every time you look up at night. Different cultures might react in different ways. Some might see it as an omen, a sign of cosmic change or renewal. Some might see it as a threat, an invasion of sorts, even though intellectually they'd understand that galaxies are just collections of stars and that the actual risk to any individual planet is small. Some might see it as an opportunity, a chance to study an unprecedented astronomical event from the inside. Religious or philosophical movements might spring up around the collision. Some might interpret it as evidence of cosmic cycles, that the universe is constantly changing and renewing itself. Some might see it as a reminder of impermanence, that even the largest structures in the universe aren't eternal. Some might see it as a call to action, a motivation to spread beyond a single planet or even a single star system to ensure survival regardless of what the merger brings. From a scientific perspective, this would be an incredible time to be an astronomer. The approaching collision would be the focus of intense study. Observatories would be monitoring both galaxies constantly, tracking their motions, measuring the developing tidal distortions, and watching for signs of increased star formation. And those signs would definitely be there by this point. The gravitational interaction between the galaxies is now strong enough to affect the distribution of gas. When gas clouds get compressed by tidal forces, they can collapse and form stars. This process is just beginning at 500 million years before contact, but it's already measurable. Astronomers would detect an uptick in the rate of star formation in both galaxies. Not a huge increase yet, not the full starburst that will come later, but a noticeable rise. More massive stars are being born, and massive stars are bright. Their formation creates glowing regions of ionized gas, visible as bright knots of light in both galaxies. The tidal distortions are also becoming visible. Remember, tidal forces arise from the difference in gravitational pull across a galaxy. The side of the Milky Way facing Andromeda feels a stronger pull than the side facing away. This stretches the galaxy, elongating it toward Andromeda. At first, this stretching is barely noticeable. But as the galaxies get closer and the gravitational forces get stronger, the effect becomes more pronounced. By 500 million years before contact, both galaxies are starting to look distorted. They're not quite the neat spiral disks they used to be. They're stretched, elongated, with the first hints of tidal tails forming, long streams of stars being pulled out of the main body of each galaxy. These tidal tails are one of the most characteristic features of colliding galaxies. When astronomers observe galaxy collisions elsewhere in the universe, they often see these long, graceful streams of stars extending from the galaxies. They're created by tidal forces, and they're a clear sign that a merger is underway. From Earth, assuming Earth still exists and hasn't been consumed by the expanding sun, the view would be surreal. Looking up, you'd see Andromeda filling a huge portion of the sky. Its spiral arms would be obvious. Its bright core would outshine everything except the moon and the brightest planets. And you might start to see distortion in the Milky Way band as well. evidence that our own galaxy is being stretched by Andromeda's gravity. The stars themselves wouldn't look different. Individual stars are too far apart to be affected by the approaching galaxy. The Sun would still look the same, though much brighter than in our era due to its gradual increase in luminosity. The planets would still be in their orbits. The constellations would look roughly familiar, though shifted slightly due to the Sun's motion through the galaxy over the intervening 500 million years. But the overall appearance of the sky would be alien. The Milky Way band, that familiar feature that's been a constant presence throughout human history, would be warped and distorted. And dominating everything would be Andromeda, a second galaxy bright and detailed, impossible to ignore. This is also when any advanced civilizations would be finalizing their preparations for the collision. 500 million years is still a long time, but it's close enough that planning needs to become action. If evacuation is necessary, it needs to happen. If infrastructure needs to be built, it needs to be built. If observations need to be made before the collision begins in earnest, they need to be made now. It's worth noting that 500 million years is roughly the amount of time it took for life on Earth to go from the Cambrian explosion, when complex multicellular life first appeared, to the present day. That's enough time for entire branches of the tree of life to evolve, flourish, and go extinct. It's enough time for continents to drift across the planet's surface, for ice ages to come and go, for mass extinctions to occur, and new forms of life to emerge. So while 500 million years sounds like an enormous amount of time, and it is by human standards, it's not infinite. For a civilization planning on a truly long-term scale, 500 million years is within the realm of actionable planning, and the visible evidence in the night sky would make the need for such planning impossible to ignore. Before we get to the actual collision, we need to talk more about dark matter, because it's playing a crucial role in everything that's happening, even though we can't see it directly. The merger of the Milky Way and Andromeda isn't just a collision of visible stars and gas, it's primarily a merger of dark matter halos, and understanding this is key to understanding how the collision will unfold. We've mentioned dark matter several times already, but let's dig deeper into what it is and why it matters so much. The story of dark matter begins in the 1930s, when astronomer Fritz Zwicky was studying the Coma cluster, a large group of galaxies bound together by gravity. He measured how fast the galaxies were moving and calculated how much mass would be needed to keep them gravitationally bound. The answer he got was strange. The galaxies were moving so fast that the visible matter, all the stars and gas he could see, wasn't nearly enough to hold the cluster together. There had to be additional mass present, mass that he couldn't see. He called it dark matter, and for decades, most astronomers dismissed the idea as unlikely. But the evidence kept accumulating. In the 1970s, astronomer Vera Rubin was studying the rotation curves of spiral galaxies. She measured how fast stars and gas were orbiting at different distances from the galactic center. According to Newton's laws of gravity, objects farther from the center should orbit more slowly, just like the outer planets in our solar system orbit the Sun more slowly than the inner planets. But that's not what Rubin found. Instead, she found that stars in the outer regions of galaxies were orbiting just as fast as stars closer to the center, sometimes even faster. This didn't make sense unless there was additional mass in the outer regions, mass that she couldn't see, dark matter. Since then, evidence for dark matter has come from many different sources. Gravitational lensing, the bending of light by gravity, shows that galaxy clusters contain much more mass than their visible matter suggests. The cosmic microwave background, the faint glow left over from the Big Bang, shows patterns that can only be explained if dark matter exists. The formation of galaxies in the early universe required dark matter to provide the gravitational seeds around which normal matter could condense. All the evidence points to the same conclusion. Dark matter makes up about 85% of all the matter in the universe. Normal matter, the stuff we're made of, the stuff that makes up stars and planets and gas clouds, only accounts for about 15% of the total matter. So, what is dark matter made of? The honest answer is we don't know. The leading hypothesis is that it's some kind of exotic particle that interacts only through gravity. These particles would pass right through normal matter without being noticed. Right now, billions of dark matter particles might be passing through your body every second, and you'd never feel them because they don't interact with the atoms in your body. Physicists have proposed various candidates for what dark matter might be. WIMPs, weakly interacting massive particles, axions, sterile neutrinos, and others. Experiments around the world are trying to detect these particles directly, but so far, none have succeeded. Dark matter remains one of the biggest unsolved mysteries in physics. But while we don't know what dark matter is, we can map where it is based on its gravitational effects. And what we've found is that every galaxy is surrounded by a massive halo of dark matter. These halos are roughly spherical, extending far beyond the visible disk of the galaxy. For the Milky Way, the visible disk is about 100,000 light-years across, but the dark matter halo extends perhaps 300,000 light-years, maybe more. The exact size is hard to pin down, because the halo doesn't have a sharp edge. It just gradually fades out, becoming less dense the farther you go from the center. Andromeda's dark matter halo is even larger, because Andromeda is a more massive galaxy. Its halo might extend 500,000 light-years or more, and these halos contain several times more mass than all the visible matter in each galaxy. Now here's the key point for the collision. The dark matter halos interact first. Long before the visible disks of the Milky Way and Andromeda touch, their dark matter halos begin to overlap and merge. At 500 million years before contact, the halos are almost certainly already interacting. At 100 million years before contact, they're deeply interpenetrating. But dark matter merges differently than normal matter. When two clouds of gas collide, they crash into each other. The atoms in one cloud collide with atoms in the other cloud. This heats the gas and creates shock waves. Energy is radiated away as light, and the gas slows down. Dark matter doesn't do any of that. Dark matter particles don't collide with each other in any meaningful way, except through gravity. When two dark matter halos merge, the particles from each halo just pass right through each other like ghosts. There are no collisions, no heating, no radiation. The dark matter particles just mix together, their trajectories affected only by the combined gravitational field of both halos. This means the dark matter merger is actually smoother and less violent than the visible merger. While the stars and gas are being thrown into chaos by tidal forces and colliding gas clouds, the dark matter just quietly blends together. But even though the dark matter merger is smooth, it's crucial because the dark matter provides most of the gravity. The visible matter, all those stars and gas clouds, responds to the gravitational field created by the dark matter. As the dark matter halos merge, they create a complex, evolving gravitational landscape, and the visible galaxies are forced to follow. Think of it like this. Imagine two invisible bowls slowly merging together. Inside each bowl, there are marbles rolling around. As the bowls merge, the shape of the combined bowl changes, and the marbles have to follow new paths. The marbles are the visible galaxies, and the bowls are the dark matter halos. The dark matter also affects the orbital dynamics of the collision. When astronomers run computer simulations of the merger, they have to include dark matter. If they only simulate the visible matter, they get completely wrong results. The galaxies don't merge properly. They bounce off each other or pass by without interacting strongly. But when they include dark matter, everything changes. The dark matter provides the gravitational glue that keeps the galaxies bound to each other. It's what causes them to fall back together after each passage. It's what eventually brings them to rest as a single merged galaxy. The distribution of dark matter also affects how tidal forces develop. Areas with more dark matter exert stronger gravitational pulls. This creates variations in the tidal forces, leading to asymmetries in the tidal tails and other features of the merger. One of the interesting things about dark matter is that we'll never see it directly. Even during the merger, even when the dark matter halos are completely mixed together, we won't see anything. Dark matter is invisible by definition, but we'll see its effects everywhere. In the motions of stars, in the shapes of tidal tails, in the timing of the collision itself. For any astronomers studying the merger, dark matter will be both a tool and a mystery. They'll use their observations of visible matter to infer the distribution of dark matter. They'll refine their models of the merger by comparing predictions to observations, and hopefully they'll learn more about the nature of dark matter itself, what it's made of, how it behaves. Whether there are different types of dark matter particles, the merger might even create opportunities to detect dark matter directly. During the collision, dark matter particles will be moving at high velocities, and some predictions suggest this could lead to increased rates of dark matter particle interactions, making them slightly easier to detect. But whether or not dark matter is ever directly detected, its role in the merger is undeniable. The collision of the Milky Way and Andromeda is fundamentally a collision of dark matter halos. The visible galaxies are just the light show, the observable manifestation of a much larger gravitational dance happening in the dark. We're now in the final countdown. Just 100 million years until first contact, and the changes are accelerating dramatically. The gravitational effects that were subtle 1 billion years ago and noticeable 500 million years ago are now intense and unmistakable. Both galaxies are showing clear signs of tidal distortion. The spiral arms are stretched and warped, no longer the neat organized structures they once were. Long tidal tails are forming, streams of stars being pulled out of the main body of each galaxy by the differential gravitational forces. These tails already extend thousands of light years, and they're growing longer by the day. The night sky at this point would be absolutely spectacular, unlike anything we can imagine from our current vantage point. Andromeda fills a huge portion of the sky, vastly larger than the Moon, its structure visible in incredible detail. But it's no longer the neat spiral galaxy it was. It's distorted, stretched, with obvious asymmetries. And the Milky Way is visibly distorted too. That familiar band of light crossing the sky is warped and irregular. In some directions, it's brighter than it used to be as stars get compressed together by tidal forces. In other directions, it's fainter as stars get pulled away into tidal tails. If you could somehow step outside both galaxies and view them from a distance, you'd see two spirals approaching each other, each one stretched toward the other, with long, graceful tails of stars streaming away from them in opposite directions. It's a sight that astronomers have observed in other galaxy mergers throughout the universe, but now it's happening to us. The gravitational chaos is also triggering increased star formation. When gas clouds get compressed by tidal forces, they can become dense enough for gravity to pull them together into new stars. At 100 million years before impact, this process is well underway in both galaxies. Star formation rates are climbing. Instead of forming a few new solar masses of stars per year, which is typical for a spiral galaxy, the Milky Way and Andromeda are now forming stars at rates several times higher, and this is just the beginning. The starburst will intensify dramatically once the galaxies actually collide and their gas clouds crash into each other. These newly formed stars are predominantly massive and hot. When a gas cloud collapses, it fragments into stars of different masses, from tiny red dwarfs to massive blue giants. But the massive stars are the ones you notice because they're so much brighter. A star weighing 20 or 30 solar masses can be tens of thousands of times more luminous than the Sun. These massive stars appear as bright blue regions in both galaxies. They're clustered together in star-forming regions, areas where gas has been compressed and is actively collapsing into new stars. These regions glow with intense ultraviolet radiation from the hot young stars, and they're some of the most prominent features visible in both galaxies at this point. From Earth, if Earth still exists, you'd see these star-forming regions as bright knots of blue light scattered throughout both the Milky Way and Andromeda. They'd be constantly changing as new massive stars form and old ones explode as supernovas. The sky would be more dynamic than it's been at any point in the past several billion years. The increased star formation also means an increased rate of supernova explosions. Massive stars live fast and die young. A star weighing 20 solar masses lives only about 10 million years before exhausting its nuclear fuel and exploding. So all these new massive stars being born now will be exploding as supernovas within just a few million years. Supernovas are among the most energetic events in the universe, briefly outshining entire galaxies. Each one releases as much energy as the Sun will emit over its entire 10 billion-year lifetime, all in just a few seconds. This energy heats the surrounding gas to millions of degrees and blasts it outward at thousands of kilometers per second. For any planets in the vicinity of these star-forming regions, the environment is becoming much harsher. The intense ultraviolet radiation from massive stars can strip away planetary atmospheres. Supernova explosions, if they occur close enough, can bathe planets in deadly radiation. This is one of the real risks of the merger for any life that happens to be present. If you're on a planet in a calm, quiet region of the galaxy, far from any active star formation, you're probably fine. But if you're in or near one of these starburst regions, the increased radiation could be dangerous. A supernova within 30 light years or so could cause serious damage to a planet's biosphere. The gravitational environment is also becoming more chaotic. Stars throughout both galaxies are having their orbits perturbed by the approaching collision. Most of these changes are subtle, small shifts in orbital parameters that won't have any immediate effect. But some stars are being kicked into dramatically different orbits. Stars on the edges of the galaxies, where the tidal forces are strongest, are most affected. Some are being pulled toward the other galaxy. Some are being flung outward, away from both galaxies, destined to become intergalactic wanderers. And some are just having their orbits scrambled, sent onto new paths that are more elliptical or more tilted relative to the galactic plane than their original orbits. This orbital scrambling is one of the main mechanisms by which spiral galaxies get transformed into elliptical galaxies during mergers. Before the collision, stars in a spiral galaxy move in fairly orderly circular orbits, all in roughly the same plane. After the collision, stars move in random directions with random orbital shapes. The organized rotation of the disk breaks down into chaotic motion. At 100 million years before impact, this process is just beginning. The spiral structure is still recognizable, but it's degrading. Within a few 100 million years, it will be completely destroyed, replaced by the more amorphous structure of an elliptical galaxy. The supermassive black holes at the centers of both galaxies are also approaching each other, though they're still separated by vast distances at this point. The Milky Way's black hole, Sagittarius A, and Andromeda's black hole are each sitting at the center of their respective galaxies, and those centers are now less than 1 million light-years apart and closing fast. As the collision progresses, these black holes will be carried along with the dense cores of each galaxy. Eventually, they'll end up orbiting each other before finally merging into a single, even more massive black hole. But that's still far in the future. At 100 million years before impact, they're still too far apart to directly influence each other. What they are doing is affecting their immediate surroundings. Both black holes are likely accreting some amount of gas, material falling toward them, and forming accretion disks. When gas falls toward a black hole, it heats up through friction and gravitational compression, becoming hot enough to emit X-rays. This makes the galactic centers more active, brighter than they would be otherwise. During the merger, as gas gets funneled toward the centers of both galaxies by gravitational forces, the black holes might become even more active. They could enter what's called an AGN, active galactic nucleus phase, where the accretion disk becomes so bright it outshines the entire rest of the galaxy. But whether this happens depends on how much gas makes it to the center, and that's difficult to predict. For any civilizations present at this time, the sky would be both beautiful and ominous. Beautiful because of the unprecedented detail visible in Andromeda, the bright star-forming regions, the graceful tidal tails, the overall sense of cosmic grandeur. Ominous because the collision is now imminent on cosmic timescales, just 100 million years away, and the visible distortions make it clear that dramatic changes are coming. This would be a society living on the brink of transformation, watching as their galaxy and their night sky prepare to change forever. So how do astronomers actually know what's going to happen during this collision? How can they predict events billions of years in the future with any confidence? The answer lies in computer simulations, and these simulations have become incredibly sophisticated over the past few decades. The basic idea is straightforward. You take the laws of physics, particularly Newton's law of gravity and Einstein's refinements to it, and you apply them to a model of two galaxies approaching each other. You start with the current positions and velocities of the Milky Way and Andromeda, and then you let the computer calculate forward in time, step by step, to see what happens. But the devil is in the details, and when you're trying to simulate something as complex as a galaxy merger, there are a lot of details to worry about. First, there's the sheer number of objects involved. The Milky Way contains somewhere between 200 and 400 billion stars. Andromeda contains about 1 trillion. If you wanted to track every single star individually, you'd need to solve the equations of motion for over 1 trillion objects, all pulling on each other gravitationally. That's computationally impossible, even with the most powerful supercomputers available. So astronomers use a trick. Instead of tracking individual stars, they track particles that each represent many stars. Think of it like this. Instead of simulating every single water molecule in a lake, you might divide the lake into millions of small parcels of water and track those. Each parcel contains billions of molecules, but you treat it as a single unit. The same approach works for galaxies. You might represent the Milky Way with 10 million particles each, one standing in for about 20 to 40 actual stars. These particles interact gravitationally, just like real stars would. They pull on each other, their trajectories change, and over billions of simulated years, the collective behavior of these millions of particles gives you a good approximation of what the real galaxy would do. But galaxies aren't just stars. They also contain gas and dust, which behave differently than stars. Stars are like individual objects that don't collide with each other. Gas, on the other hand, can collide, compress, heat up, and cool down. It can form new stars. It responds to pressure and turbulence, not just gravity. To simulate gas, astronomers use different techniques. One common approach is called SPH, Smoothed Particle Hydrodynamics. In SPH, gas is represented by particles, similar to how stars are represented, but these gas particles can interact with each other directly. When two gas particles get close, they can collide, exchange energy and momentum, and heat up. The simulation tracks the temperature, density, and velocity of each gas particle and uses this information to determine how the gas behaves. Another approach is to use a grid. You divide space into millions of tiny cubic cells and track the gas properties in each cell. Gas can flow from one cell to another, creating currents and turbulence. This method is called Eulerian hydrodynamics, and it's particularly good at capturing the details of how gas behaves during collisions. Then there's dark matter. Remember, dark matter makes up most of the mass of each galaxy, so it's crucial to include it in the simulation. Dark matter is actually easier to simulate than gas. because dark matter particles don't interact with each other except through gravity. They just pull on each other gravitationally and follow their trajectories. So you can represent dark matter with particles, just like stars, and track their motion through the simulation. A typical modern simulation of a galaxy merger might include 10 million particles representing dark matter, 10 million representing stars, and a few million representing gas. Each particle pulls on every other particle gravitationally, though in practice, various computational tricks are used to speed up these calculations. One such trick is called a tree algorithm. Instead of calculating the gravitational force from every single particle on every other particle, which would require trillions of calculations per time step, the algorithm groups distant particles together. If a bunch of particles are far away from the particle you're interested in, you treat them as a single object located at their center of mass. This drastically reduces the number of calculations needed while still giving accurate results. The simulation then steps forward in time. You calculate all the forces on all the particles at a given moment, determine how much each particle should move in a short time interval, maybe a few thousand years of simulated time, move all the particles accordingly, and then repeat. Step by step, you march forward through billions of years of simulated time. Modern simulations can take weeks or even months to run on powerful supercomputers, even with all these optimizations. The computers being used are massive machines with thousands of processors working in parallel. Each processor handles a portion of the simulation, calculating the forces and motions for a subset of particles, and the results are combined to get the full picture. The simulations have become remarkably sophisticated. They can track not just the motion of stars and gas, but also star formation, supernova explosions, black hole growth, and the heating and cooling of gas. When gas gets compressed during a collision, the simulation can determine whether conditions are right for new stars to form. When massive stars die as supernovas, the simulation can inject energy back into the surrounding gas, heating it and driving winds. So, how reliable are these simulations? The short answer is pretty reliable for the big picture, less certain for the details. The overall trajectory of the collision is well constrained. Different research groups have run simulations of the Milky Way Andromeda merger, and they all agree on the basic outcome. The galaxies will collide, pass through each other multiple times, and eventually merge into a single elliptical galaxy. The timing is also fairly consistent across simulations, with first contact happening in roughly 4 to 4.5 billion years. Where the simulations differ is in the details, the exact shapes of the tidal tails, the precise rate of star formation during the starburst, the final structure of the merged galaxy. These things vary from one simulation to another, depending on the exact assumptions and methods used. Part of the uncertainty comes from things we don't know precisely. We don't know the exact mass of either galaxy. We don't know the exact distribution of dark matter in their halos. We don't know if there are significant amounts of hot gas in the space between the galaxies that might affect the collision. We don't know the exact orientations and rotation states of the galaxies relative to each other. Small changes in these parameters can lead to noticeable differences in the outcome. A slightly different angle of approach might create longer or shorter tidal tails. A slightly different mass ratio might change how much star formation is triggered. These are second-order effects. They don't change the fundamental conclusion that a merger is coming, but they do affect the details of what it will look like. Another source of uncertainty is the physics itself. Simulating star formation is particularly challenging because it happens on very small scales, within giant molecular clouds, scales that are much smaller than the resolution of a galaxy-scale simulation. So star formation has to be approximated using simplified rules, and different simulations use different rules. The same is true for supernova feedback, the process by which exploding stars inject energy into the surrounding gas. How much energy gets injected, how far it spreads, how it affects subsequent star formation, these are all uncertain. Different simulations make different assumptions, and this leads to different predictions for the starburst intensity. Black hole physics is another area of uncertainty. When gas falls toward a supermassive black hole, some of it gets accreted, adding to the black hole's mass, but some of it gets heated and blown away in powerful winds. The balance between these processes determines how fast the black hole grows and how much energy it injects into the galaxy. Simulating this accurately requires tracking processes on scales from the event horizon of the black hole, measured in light hours, to the entire galaxy, measured in thousands of light years. A range of scales that's almost impossible to capture in a single simulation. Despite these uncertainties, the simulations have been validated in several ways. Astronomers can compare the simulations to observations of other galaxy mergers happening elsewhere in the universe. There are thousands of galaxy mergers visible at various stages, from initial approach to final coalescence. By comparing simulations to these observations, astronomers can tune their models and verify that they're producing realistic results. The simulations also make testable predictions. For example, simulations predict certain features in the distribution of stars in galaxies that have undergone past mergers. Features like stellar streams and shells. When astronomers look carefully at galaxies, including our own Milky Way, they find exactly these features, remnants of smaller galaxies that were absorbed in the past. This gives us confidence that the simulations are capturing the real physics. Over the past few decades, simulations have gotten better and better as computers have become more powerful and our understanding of the physics has improved. Early simulations in the 1970s and 80s were crude, tracking only a few thousand particles and ignoring gas and star formation entirely. But they got the basic picture right. Galaxies collide, they pass through each other multiple times, and they eventually merge. Modern simulations, with millions of particles and sophisticated physics, are refining that picture, adding detail and nuance. We now understand that the starburst is triggered by gas collisions, that tidal tails form from differential gravitational forces, that the final merged galaxy is an elliptical, and that the supermassive black holes eventually merge. One of the most interesting results from simulations is the prediction of how individual stars will be affected. By tracking the trajectories of particles through a simulated merger, astronomers can calculate statistics like what fraction of stars end up in the central bulge of the new galaxy, what fraction get thrown into the outer halo, what fraction get ejected entirely. The answers are somewhat probabilistic. It depends on where a star starts, how it moves through the merger, and what gravitational encounters it experiences along the way. But statistically, the simulations suggest that most stars, maybe 60 to 70%, will end up in the main body of the merged galaxy. About 20 to 30% will end up in the outer halo, and a small fraction, maybe 1 to 5%, will be ejected completely, flung out into intergalactic space. These are the kinds of predictions that will be testable, in a sense, after the merger happens. Of course, none of us will be around to check, but if there are astronomers in Milky billions of years from now, they'll be able to look at the distribution of stars and compare it to what the simulations predicted. It would be the ultimate validation of our models. So when astronomers say that the Milky Way and Andromeda will collide in 4 billion years and merge into an elliptical galaxy, they're not just guessing. They're basing this on detailed simulations that incorporate our best understanding of physics, run on powerful supercomputers, and validated against observations of other galaxy mergers throughout the universe. The prediction is as solid as any prediction about the distant future can be. Let's talk about the moment of first contact, because it's not quite what most people imagine when they hear the word collision. When two cars collide, it's violent and immediate. Metal crumples. Glass shatters. The cars bounce off each other or stick together in a twisted wreck. It happens in seconds. And when most people hear that two galaxies are going to collide, they picture something similar: a catastrophic crash, explosions, chaos. But galaxy collisions don't work like that. In fact, collision might not even be the right word. Merger is more accurate, but even that doesn't fully capture what happens. The process is slow, gentle in a way, even though the forces involved are enormous. Here's the key thing to understand. Galaxies are mostly empty space. Incredibly, almost incomprehensibly empty. Let's put this in perspective. The Sun's nearest stellar neighbor is Proxima Centauri, about 4.2 light-years away. That's roughly 25 trillion miles. If you scaled the Sun down to the size of a grain of sand, Proxima Centauri would be another grain of sand about 4 miles away. And in between, nothing. Just empty space. That's typical for the spacing between stars in our region of the galaxy. In denser regions, near the galactic center, stars are closer together, maybe a light-year apart on average. In the sparse outer regions, they're even farther apart than Proxima Centauri. Now imagine two swarms of objects approaching each other, where each object is separated from its nearest neighbor by distances of 4 miles or more, but the objects themselves are the size of grains of sand. When these two swarms interpenetrate, what are the chances that any 2 grains of sand actually hit each other? Almost zero. This is what happens when galaxies collide. The galaxies pass through each other, their stars interpenetrating, mixing together. But individual stellar collisions are extraordinarily rare. The space between stars is so vast that they just sail past each other, like 2 clouds of gnats passing through each other, without any individual gnats colliding. Astronomers have calculated the odds of stellar collisions during a galaxy merger. The number varies depending on where you are in the galaxy and how the collision unfolds. But in typical regions, the probability of any individual star directly hitting another star is something like 1 in a trillion, or even lower. To put that in perspective, the Milky Way contains roughly 300 billion stars. Andromeda contains about 1 trillion. If the probability of collision is 1 in a trillion, you'd expect maybe 1 stellar collision during the entire merger. Possibly none. Even in the densest regions, near the galactic cores where stars are packed much more tightly, collisions are still rare. You might get a few dozen stellar collisions, maybe a few hundred. Out of 1 trillion stars, that's statistically irrelevant. So the first pass, when the 2 galaxies initially overlap, doesn't involve explosions or destruction. It's more like 2 ghost galaxies passing through each other. The stars from each galaxy move through the space occupied by the other galaxy, barely noticing the stellar population of the other side. But just because the stars don't physically collide doesn't mean nothing happens. Far from it. The gravitational effects are enormous. Every star in each galaxy is pulling gravitationally on every star in the other galaxy. This doesn't cause collisions, but it does change trajectories. A star from the Milky Way might be pulled slightly toward a clump of stars from Andromeda. Its path bends. Its velocity changes. It ends up on a different trajectory than it would have followed otherwise. Multiply this effect by hundreds of billions of stars, all pulling on each other, and you get chaos. The neat, organized motion that characterized both galaxies before the collision breaks down. Stars that were following circular orbits around the galactic center get kicked into elliptical orbits. Stars that were moving in the plane of the disk get tilted out of the plane. This is gravitational scattering, and it's the primary mechanism by which galaxy mergers scramble the stellar populations of both galaxies. It doesn't require physical collisions. It just requires gravity acting over time. The first pass happens relatively quickly by cosmic standards. The galaxies are approaching each other at about 250,000 miles per hour, possibly faster as they get closer, and their mutual gravity accelerates them. At that speed, it takes only a few tens of millions of years for them to pass completely through each other. Tens of millions of years sounds long, and by human standards it is. But in cosmic terms, it's fast. It's less than the lifetime of a massive star. It's much less than the orbital period of the Sun around the galactic center. On galactic timescales, the first pass is like a quick encounter, over almost before you realize it's begun. But during those tens of millions of years, a tremendous amount happens. The tidal forces, which have been building for hundreds of millions of years as the galaxies approached, reach their peak intensity during the first pass. This is when the tidal tails, those long streams of stars pulled from each galaxy, grow most rapidly. Imagine you're a star on the outer edge of the Milky Way, on the side facing Andromeda. As Andromeda passes by, you feel an enormous gravitational pull from it. You're yanked away from the main body of the Milky Way, pulled toward Andromeda, but you don't fall into Andromeda. Instead, you're flung into a new orbit, one that takes you far from both galaxies. You become part of a tidal tail, a stream of stars that extends hundreds of thousands of light years into space. You're still gravitationally bound to the system, the combined Milky Way-Andromeda system, but you're no longer part of either galaxy's main body. You're in a sort of limbo, orbiting in the space between and around the galaxies. These tidal tails are some of the most visually striking features of colliding galaxies. When astronomers photograph galaxy mergers elsewhere in the universe, the tidal tails are often the first thing that catches the eye. They're long, graceful arcs of stars, curving through space like cosmic streamers. The shape of the tidal tails depends on the geometry of the collision. If the galaxies are rotating when they collide, the tidal tails curve, tracing out spirals. If the collision is head-on, the tails might be straighter. Computer simulations can reproduce these shapes, and by comparing simulations to observations, astronomers can figure out the details of how a particular merger unfolded. For the Milky Way-Andromeda collision, simulations predict that we'll develop prominent tidal tails during and after the first pass. These tails will contain millions, possibly billions of stars, pulled from both galaxies and stretched into long arcs extending far beyond the main bodies of the merging galaxies. Now, while the stars pass through each other like ghosts, the gas is a different story. Gas clouds can collide, and when they do, it's dramatic. Gas is much more diffuse than stars. The interstellar medium, the gas between the stars, has a density of maybe 1 atom per cubic centimeter in typical regions. That's far, far less dense than any vacuum we can create on Earth. But it's dense enough that when two clouds of gas collide at high velocities, they interact. The collision compresses the gas, squeezing it into a smaller volume. This compression heats the gas, raising its temperature. And if the gas gets compressed enough, it becomes dense enough for gravity to pull it together into clumps that will eventually collapse into new stars. This is the beginning of the starburst, the intense period of star formation triggered by the merger. We'll talk more about the starburst later, but during the first pass, it's just starting. Gas clouds from the two galaxies are beginning to collide, and the first wave of new star formation is being triggered. The first pass also marks the moment when the two galactic cores pass closest to each other. The cores are the dense central regions of each galaxy, containing a large fraction of each galaxy's stellar mass, and, at the very center, the supermassive black holes. When the cores pass by each other, separated by maybe a few tens of thousands of light years, the gravitational interaction is intense. Stars in the cores feel enormous tidal forces. Some get kicked into high-velocity orbits. Some get pulled from one core toward the other. The cores themselves might be visibly distorted, elongated by the mutual tidal forces. But the cores don't merge during the first pass. They're moving too fast. They just sweep past each other and continue on their separate trajectories. It will take multiple passes and a lot of dynamical friction before the cores finally sink together and merge. For any observers watching the first pass, assuming they're in a safe location not too close to the most chaotic regions, it would be an incredible sight. The two galaxies, which have been approaching each other for billions of years, finally overlap. You'd see stars from both galaxies mixing together in the sky. The density of stars would be noticeably higher in some directions, as the two populations combine. Andromeda's bright central core would be clearly visible, a brilliant concentration of light moving across the sky over millions of years. The Milky Way's core would be visible in the opposite direction, and connecting them, threading through the space between them, you'd see the complex structure of both galaxies interpenetrating. It would be clear that something extraordinary was happening. The sky would be changing on timescales short enough that careful observers would notice. Over a single human lifetime, star positions would shift noticeably. New structures would appear. The tidal tails would grow and evolve. But on the ground, on any planet, life would probably continue normally. The nearest stars from the other galaxy would still be light years away. There would be no immediate danger, no sudden catastrophe, just a slowly changing sky and the knowledge that your galaxy was in the process of merging with another. After the first pass, the galaxies continue moving. They don't stick together. They separate again, pulled apart by their own momentum. But they're gravitationally bound to each other now, if they weren't already before. They'll swing back together for a second pass, and a third, and as many passes as it takes for them to finally lose enough energy to settle into a single merged structure. During the first pass, the gravitational disruptions reach their peak intensity, and the consequences are spectacular and chaotic. This is when the organized structure of both galaxies truly begins to break down, replaced by turbulence on a scale that's hard to fully comprehend. Let's start with what happens to individual stars. Before the collision, a typical star in a spiral galaxy follows a fairly predictable orbit. It moves in a roughly circular path around the galactic center, staying in or near the plane of the disk. Its orbit might take a few 100 million years to complete, but it's stable and consistent. During the first pass, all that changes. The star suddenly finds itself in a gravitational environment that's much more complex than before. It's not just feeling the pull of its home galaxy anymore. Now it's also feeling the pull from the other galaxy, and that pull is constantly changing as the galaxies move relative to each other. The result is that the star's orbit gets perturbed. It might be pulled into a more elliptical orbit, swinging closer to the galactic center, and then farther out. It might be kicked out of the plane of the disk, ending up on an orbit that's tilted relative to its original path. Or it might be thrown into an entirely new trajectory, sent toward the opposite galaxy, or flung outward into the space beyond both galaxies. This happens to stars throughout both galaxies, though the effects are strongest in the outer regions, where tidal forces are most intense. Stars near the centers of the galaxies are more strongly bound by the gravity of their own galaxy, and are less easily disrupted, though they're still affected. The overall effect is that the neat, organized motion of a spiral galaxy gets scrambled into the chaotic, random motion characteristic of an elliptical galaxy. Instead of all stars moving in the same direction in roughly circular orbits, you end up with stars moving in all directions on orbits of all different shapes. This scrambling is exactly what we see when we observe elliptical galaxies. The stars in an elliptical galaxy move in what appears to be random directions. There's no organized rotation, no preferred plane of motion, and the reason elliptical galaxies look like this is because most of them formed from mergers where the original organized motion was destroyed by gravitational chaos. Now let's talk about the tidal tails in more detail, because they're one of the most dramatic consequences of the first pass. We've mentioned them before, but during the first pass, they really come into their own. Tidal tails form because of the difference in gravitational force across each galaxy. The side of the Milky Way closest to Andromeda feels a stronger pull than the far side. This difference stretches the galaxy, pulling stars away from the main body. But here's what's interesting. The tidal tails don't just point directly toward and away from the other galaxy. They curve, forming graceful arcs. This happens because the galaxies are rotating as they collide. The rotation adds a sideways component to the motion of stars being pulled into the tails, causing them to spiral outward rather than moving in straight lines. Computer simulations show that the tidal tails can extend for hundreds of thousands of light years, possibly even more than 1 million light years. They contain millions of stars, maybe billions, all following similar trajectories through space. If you could see these tails from a distance, they would look like cosmic streamers, elegant and beautiful despite the violent forces that created them. These tails are temporary structures over hundreds of millions of years. As the galaxies continue to interact and eventually merge, the tails will gradually be reabsorbed. Stars in the tails will fall back toward the main body of the merged galaxy, pulled in by gravity. But during the merger itself, the tails are prominent and persistent features. For any astronomers observing from within one of the galaxies, the tidal tails would be visible as diffuse streams of stars stretching across the sky. They might be faint, because the stars in them are spread out over such large volumes, but with telescopes, they would be clearly detectable. The spiral arms, those beautiful structures that define spiral galaxies, are being destroyed during the first pass. Spiral arms are density waves, regions where stars and gas are temporarily more concentrated as they orbit. They're maintained by the organized rotation of the galactic disk. But when you introduce the chaotic gravitational environment of a merger, the organized rotation breaks down. The density waves that create spiral arms can't persist. Instead, the arms get stretched, twisted, and eventually shredded completely. By the end of the first pass, the spiral structure is already badly disrupted. You might still see hints of the original arms, but they're distorted and irregular. Within a few more orbital passages, the spiral structure will be completely gone, replaced by the more amorphous, featureless appearance of an elliptical galaxy. This is actually a bit sad from an aesthetic perspective. Spiral galaxies are beautiful, with their elegant arms and organized structure. Elliptical galaxies are less visually striking, just smooth, roughly spherical collections of stars. The merger trades beauty for chaos, though of course, that's a human aesthetic judgment. The universe doesn't care how galaxies look. Gas clouds are colliding during the first pass, and these collisions are genuinely violent. Unlike stars, which pass through each other without touching, gas clouds crash together, and the results are dramatic. When two gas clouds collide at velocities of hundreds of kilometers per second, the kinetic energy of their motion gets converted into heat. The gas heats up, sometimes to temperatures of millions of degrees. At these temperatures, the gas glows in X-rays, creating bright regions visible to X-ray telescopes. But not all the gas gets heated to such extreme temperatures. In some regions, the collision compresses the gas without heating it too much. These compressed regions are exactly what's needed to trigger star formation. Remember, star formation requires gas to be dense and cold. When a gas cloud is compressed by a collision, its density increases dramatically. If the gas can radiate away its heat quickly enough, it stays cold despite the compression. This creates ideal conditions for gravitational collapse. So, during the first pass, while some gas is being heated and dispersed, other gas is being compressed into dense clumps that will form new stars. This marks the beginning of the starburst phase, which we'll discuss in more detail later. The gas collisions also create shock waves, regions where the gas transitions abruptly from moving at one velocity to moving at another. Shock waves are common in astrophysics. Supernova explosions create shock waves, stellar winds create shock waves, and galaxy collisions create enormous shock waves that propagate through the gas at supersonic speeds. These shock waves can trigger additional star formation by compressing gas as they pass through. They can also heat gas, potentially disrupting star formation. The interplay between compression and heating is complex, and it's one of the factors that determines how much star formation is triggered by the merger. Star formation isn't uniform throughout the galaxies. It's concentrated in specific regions where the gas is densest and where collisions are most intense. These regions light up as bright blue star-forming regions, visible even from great distances. From within the galaxies, these star-forming regions would appear as bright nebulae, glowing clouds of gas lit from within by newly formed stars. They'd be scattered throughout both galaxies, more numerous in some areas than others, creating a patchy, irregular appearance. The supermassive black holes at the centers of both galaxies are also affected by the first pass, though their evolution is slower and more gradual. As the galactic cores pass by each other, gas gets disturbed and some of it starts falling toward the black holes. When gas falls toward a black hole, it forms an accretion disk, a swirling disk of material orbiting the black hole at high speeds. Friction within the disk heats it to enormous temperatures, causing it to glow brightly. The black hole becomes what's called an active galactic nucleus, or AGN. Whether both black holes become active during the first pass depends on how much gas makes it to the centers of the galaxies. If a lot of gas is funneled inward by the tidal forces, the black holes could become very active, possibly outshining the rest of the galaxy. If less gas makes it to the center, the black holes might remain relatively quiet. This is one of the uncertainties in predicting the merger. We don't know exactly how much gas will be funneled to the centers, and we don't know exactly how the black holes will respond. But it's possible, even likely, that at least one of the black holes will go through an active phase during the merger. The gravitational chaos during the first pass also affects any planets and planetary systems. We've said that stellar collisions are rare, and that's true, but gravitational perturbations are common. A star from the other galaxy might pass within a few light years of the Sun, and that's close enough to disturb the Oort cloud. The Oort cloud is a vast shell of comets surrounding the solar system at a distance of about 1 light-year. These comets are only barely held by the Sun's gravity. A passing star can nudge them, knocking some into orbits that send them plunging towards the inner solar system. This could create a period of increased comet impacts, a comet shower lasting for millions of years. For any planets with life, including potentially Earth if it's still habitable, this could be hazardous. Large comet impacts can cause extinction events, destroy ecosystems, and fundamentally alter planetary climates. But again, the odds of any specific planetary system being affected are low. Most stars, including probably the Sun, will pass through the first encounter without any close approaches from other stars. The distances are just too large for close encounters to be common. The first pass is over in a few tens of millions of years, but its effects last much longer. The tidal tails continue to stream away from the galaxies. The scrambled stellar orbits remain scrambled. The triggered star formation continues for millions of years after the initial collision. And the galaxies, now separated again, begin the long swing back toward each other for the second pass. This is the question everyone wants answered. What happens to Earth during the collision? What happens to the Sun, the planets, our solar system as a whole? The answer is both reassuring and unsettling, depending on what you consider important. Let's start with the most immediate concern. Will Earth be destroyed in a collision with another star? The answer is almost certainly no. The chances of a stellar collision are extraordinarily low, as we've discussed. Stars are so far apart that even during a galaxy merger, when stellar densities increase somewhat, collisions remain incredibly rare. To put a number on it, astronomers have calculated that the probability of the Sun directly colliding with another star during the merger is something like 1 in a trillion, or even lower. That's essentially 0 for practical purposes. You're vastly more likely to win the lottery multiple times in a row than to experience a stellar collision during the merger. Even close approaches are rare. The probability of another star passing within 1 light-year of the Sun during the merger is low, maybe a few percent at most. The probability of a star passing within the orbit of Neptune, which would be close enough to potentially disrupt the planetary system, is even lower, well under 1%. So Earth almost certainly won't be destroyed by a direct collision or close encounter. The solar system will survive the merger intact, at least in terms of its basic structure. The planets will remain in their orbits around the Sun, held by the Sun's gravity, which is far stronger than any external gravitational perturbations. But that doesn't mean nothing changes. Far from it. While the solar system itself remains intact, its location within the galaxy will change dramatically, and that has important consequences. Right now, the Sun orbits around the center of the Milky Way, at a distance of about 26,000 light-years. We're in a fairly calm region, between spiral arms, where the density of stars is moderate and the environment is stable. We complete one orbit around the galactic center every 225 million years or so, following a roughly circular path. During the merger, that orbit is going to be completely disrupted. The Sun will be pulled and pushed by the gravitational forces from both galaxies. Its trajectory will change. Its orbital energy and angular momentum will be exchanged with other stars through gravitational interactions. By the time the merger is complete, the Sun will be on an entirely different orbit than it is today. Where exactly will we end up? That's impossible to predict with certainty because it depends on the chaotic details of how the merger unfolds. But we can talk about probabilities. Computer simulations that track the fates of individual stars during galaxy mergers give us statistical predictions. According to these simulations, most stars, maybe 60 to 70%, end up in the main body of the merged galaxy. They're pulled around by the gravitational chaos, their orbits scrambled, but they remain part of the galaxy's primary structure. About 20 to 30% of stars end up in the outer halo of the merged galaxy. These are stars that got kicked into orbits that take them far from the galactic center. They still orbit the merged galaxy, but at large distances, tens or even hundreds of thousands of light-years from the center. And a small fraction, maybe 1 to 5%, get ejected entirely. These stars are kicked so hard that they reach escape velocity. They leave the galaxy altogether, becoming intergalactic wanderers. So there's roughly a 2/3 chance we end up somewhere in the main body of the new galaxy. Maybe a 1/4 chance we end up in the halo, and a small but non-zero chance we get ejected completely. What would these different fates look like from Earth's perspective, assuming Earth still exists? If we end up in the main body of the merged galaxy, life continues in a broadly similar way. We'd still be orbiting within a galaxy, surrounded by other stars, with the galactic plane and galactic center visible in our sky. The details would be different. The galaxy would be elliptical rather than spiral. The stellar density might be higher or lower depending on exactly where we end up, and the night sky would look completely different because all the constellations would be scrambled. But fundamentally, we'd still be in a galaxy, still part of a larger structure, still experiencing a night sky with stars and a diffuse glow from the galactic background. If we end up in the halo, things would be quieter and more isolated. The halo is sparsely populated compared to the main body of a galaxy. Stars are much farther apart. If the Sun ends up in the halo, our nearest stellar neighbors might be tens or even hundreds of light-years away, much farther than the current distance to Proxima Centauri. From Earth, the night sky would be dominated by the glow of the merged galaxy, visible as a large, bright region in the sky. Instead of being inside the galaxy looking out, we'd be outside looking in. The galaxy would be a distant object, beautiful and impressive, but separate from us. If we get ejected entirely, the night sky would become very dark. We'd be traveling through intergalactic space, with no galaxy nearby. The merged Andromeda galaxy would be visible as a bright smudge in the distance, slowly receding as we moved away from it. Other nearby galaxies, like those in the local group, might be visible as faint patches, but overall the sky would be much darker than it is today, with fewer stars and less structure. This might sound lonely, but it's worth noting that the Sun would still be the Sun, and Earth would still be Earth. From day to day, life on Earth, if any still exists, would continue normally. The Sun would still provide light and heat. The seasons would still change. The moon would still orbit. The only difference would be what you see when you look up at night. Now, there's another important factor to consider. Earth probably won't be habitable by the time the merger happens anyway. Remember, the sun is gradually getting brighter over time. Within about 1 billion years, maybe two at most, Earth will become too hot for liquid water to exist on the surface. The oceans will evaporate, and Earth will transform into a Venus-like world with a thick atmosphere and scorching temperatures. By 4 billion years from now, when the merger begins, Earth will almost certainly be a lifeless, barren planet. Any life that originated on Earth will either be extinct or will have moved elsewhere, to Mars, to habitats in the outer solar system, to other star systems, or into forms we can't currently imagine. So when we ask what happens to Earth during the merger, the honest answer is that Earth, the planet, will probably survive physically, but Earth, the living world, Earth as a habitat for life, will already be long gone for reasons having nothing to do with the collision. The same is true for the other planets. Venus and Mercury will likely be engulfed when the Sun eventually expands into a red giant, which will happen within 1 billion years or so after the merger. Mars will survive, but will be heated significantly by the brighter Sun. The gas giants, Jupiter, Saturn, Uranus, and Neptune, will survive with relatively little change, though they might lose some of their outer atmospheres to the increased solar radiation. What about the Sun itself? The merger doesn't affect the Sun's internal evolution. The Sun is powered by nuclear fusion in its core, converting hydrogen into helium. This process is determined entirely by the Sun's mass and composition. External gravitational forces from the galaxy don't change how fast the Sun burns its fuel. By 4 billion years from now, the Sun will be nearing the end of its main sequence lifetime. It will still be fusing hydrogen, but it will be brighter and hotter than it is today. Within another 1 billion years after the merger, the Sun will exhaust the hydrogen in its core and begin transforming into a red giant. So the Sun's fate is sealed by its own internal processes, not by the merger. The merger changes where the Sun is located, what orbit it follows, what it sees in the night sky. But it doesn't change the Sun's fundamental evolution. There is one scenario worth considering. What if the Sun ends up near a region of intense star formation during the merger? Star-forming regions are full of massive young stars that emit intense ultraviolet radiation. They're also sites of frequent supernova explosions. If the Sun happens to pass close to one of these regions, it could be exposed to dangerous levels of radiation. A nearby supernova, within 30 light-years or so, could bathe the solar system in X-rays and gamma rays, potentially damaging any planetary atmospheres or life that might still exist. But this is a low-probability scenario. The star-forming regions, while bright and active, occupy a small fraction of the total volume of the merging galaxies. Most stars, including probably the Sun, will never get close to these dangerous areas. Another consideration is the Oort cloud. During the chaotic gravitational environment of the merger, especially during the first few passes when the galaxies interpenetrate, there's an increased chance of other stars passing relatively near the Sun. Even a passage at a distance of a few light-years could disturb the Oort cloud, sending comets plunging toward the inner solar system. This could increase the rate of comet impacts on Earth and the other planets. How much of an increase? That depends on how many close stellar passages occur, and that's difficult to predict. But estimates suggest the impact rate could go up by a factor of several, maybe even 10 or more during the most chaotic phases of the merger. For Earth, if it was still habitable, this could be a serious threat. Large comet impacts can cause mass extinctions. An increased bombardment rate sustained over millions of years could make the surface of Earth uninhabitable, even if it was otherwise suitable for life. But again, by the time the merger happens, Earth will probably already be uninhabitable for other reasons. So, the comet bombardment, while interesting from a scientific perspective, isn't really the main threat to Earth. The bottom line is this: the solar system will almost certainly survive the merger physically intact. The sun and planets will still be together, bound by mutual gravity. But where we are in the galaxy will change dramatically. We might end up closer to the center, farther from the center, or even ejected entirely. And the sun's long-term evolution, its gradual brightening and eventual expansion into a red giant, will make Earth uninhabitable long before the merger begins. So the merger isn't really a threat to Earth in the way people might fear. It's not going to destroy the planet or cause immediate catastrophe, but it is going to change our cosmic address, our place in the universe, in ways that are profound, even if they don't affect daily life. Let's paint a picture of what the night sky would actually look like during the first passage, because it would be one of the most spectacular sights imaginable. This is the moment when the two galaxies overlap, when stars from both populations are mixed together, and when the sky is filled with evidence of the cosmic transformation underway. First, imagine you're standing somewhere in the solar system with a view of the night sky. Maybe you're on Earth, though as we've discussed, Earth is probably uninhabitable by this point. Maybe you're on a space habitat, or a colony on a moon of Jupiter, or a planet around another star. Wherever you are, you're about to witness something extraordinary. The most immediately obvious feature would be Andromeda. No longer distant, no longer small, Andromeda now fills a huge portion of the sky. Its bright central core is one of the most prominent objects visible, rivaling or even exceeding the brightness of the full moon. You can see individual bright stars within it, massive supergiants that shine with the light of tens of thousands of suns. The spiral structure of Andromeda, which was already visible before the collision, is now in the process of being destroyed. The arms are stretched and distorted, no longer following smooth curves. They're being pulled apart by tidal forces, creating irregular structures that shift and change over time. But even in their disrupted state, the spiral arms are beautiful. They're dotted with bright blue regions, massive star-forming areas where new stars are being born. These regions glow with intense light, visible even across the vast distances separating us from Andromeda. Each one is a stellar nursery containing thousands or millions of new stars. Threading through Andromeda, you'd see dark lanes of dust, regions where dense clouds of gas and dust block the light from stars behind them. These dust lanes create a complex pattern of light and shadow, adding depth and structure to the galaxy's appearance. The tidal tails would be visible, stretching away from Andromeda in graceful arcs. They'd be fainter than the main body of the galaxy because the stars in them are spread out over such large volumes. But with the naked eye or simple binoculars, you'd be able to trace their paths across the sky. Now look in the opposite direction, toward the center of what used to be the Milky Way. You'd see our own galaxy's core, also bright and prominent, but distorted in similar ways. The Milky Way's spiral structure, which we normally see edge on as a band across the sky, would be warped and irregular. Stars from both galaxies would be mixed together throughout the sky. In some directions, you'd see enhanced stellar density as populations from both galaxies overlap. In other directions, you'd see gaps where tidal forces have pulled stars away, leaving regions that are less densely populated than before. The constellations you grew up with, assuming you're in a civilization that has constellations, would be completely unrecognizable. The familiar patterns of stars have been scrambled by billions of years of orbital motion and by the gravitational chaos of the merger. New patterns might be visible, formed by chance alignments of bright stars, but they'd have no connection to the constellations of the past. Between the two galactic cores, threading through the space where the galaxies are interpenetrating, you'd see complex structures, streams of stars, bridges of light connecting one galaxy to the other, regions of enhanced brightness where stellar populations overlap. It would look chaotic, almost turbulent, a sky in the process of transformation. The star-forming regions would be scattered throughout both galaxies, appearing as bright blue knots of light. Some would be small, just a few light years across. Others would be enormous, spanning hundreds or thousands of light years, containing enough mass to form millions of stars. Each one would glow with the combined light of countless young, hot stars. These star-forming regions would also be surrounded by glowing nebulae, clouds of gas that have been heated and ionized by the intense ultraviolet radiation from the massive stars within them. The nebulae would glow in characteristic colors: red from ionized hydrogen, green from ionized oxygen, blue from scattered light. They'd be some of the most colorful and visually striking objects in the sky. You might also see evidence of supernova explosions. Massive stars live fast and die young, and in the star-forming regions, stars massive enough to explode as supernovas are being born constantly. Within just a few million years, many of them will have already exploded. A supernova is bright enough to be visible across the entire galaxy. For a few weeks, a single exploding star can rival the brightness of its entire host galaxy. If you're watching the sky carefully, you might see several supernovas in a single human lifetime. Bright points of light that suddenly appear, brighten dramatically, and then fade over the course of weeks or months. After a supernova, you'd be left with a supernova remnant, an expanding shell of gas blown away from the exploding star. These remnants glow in X-rays and visible light, creating intricate, beautiful structures that expand over thousands of years. The Milky Way band, that familiar feature that's been a constant in Earth's sky for billions of years, would be completely transformed. Instead of a smooth, continuous band, you'd see an irregular, patchy structure, warped and distorted by the merger. In some places it would be brighter than before. In other places it would fade away entirely. And running alongside the Milky Way band, or crossing it, or merging with it depending on your viewing angle, you'd see the structure of Andromeda. 2 galaxies worth of stars, all visible in the same sky, creating a complex tapestry of light. If you had access to different wavelengths beyond visible light, the view would be even more spectacular. In infrared, you'd see the cool dust that permeates both galaxies, glowing with thermal radiation. Infrared would also pierce through the dust, revealing star-forming regions hidden from view in visible light. In ultraviolet, the hot young stars would stand out dramatically. UV observations would show you where the most intense star formation is occurring, where the most massive stars are located, and where the radiation is most intense. In X-rays, you'd see the hot gas, regions where gas has been heated to millions of degrees by supernova explosions or by compression during the collision. You'd also see the supermassive black holes at the centers of both galaxies, if they're actively accreting matter. They're accretion disks glowing brilliantly in X-rays. The Moon, if you're viewing from Earth or somewhere in the solar system where the Moon is visible, would look the same as always. The merger doesn't affect the Moon. It would still reflect sunlight, still go through its phases, still be a constant, familiar presence, even while everything else in the sky is transformed. The planets would also be unchanged. Jupiter, Saturn, Venus, Mars, they'd still be visible as bright points of light, moving against the background stars, just as they always have. Their motions are determined by their orbits around the Sun, and those orbits are unaffected by the distant gravitational forces of the merging galaxies. But the background against which the planets move would be completely different. Instead of familiar constellations, they'd be moving through unrecognizable star fields, through the mixed stellar populations of 2 galaxies in collision. From certain locations in the galaxy, the view would be even more dramatic. If you were closer to one of the galactic cores, near the regions where stellar density is highest, the sky would be crowded with stars. Instead of a few thousand stars visible to the naked eye as we see from Earth today, you might see tens of thousands, or even hundreds of thousands of stars, packed so densely that the sky would glow with their combined light. Or, if you were in one of the tidal tails far from the main bodies of both galaxies, you'd see a different kind of beauty. The tidal tails are less dense than the galactic disks, so there would be fewer nearby stars. But looking back toward the main bodies of the merging galaxies, you'd have an external view of the collision, watching from outside as the two galaxies interpenetrate and merge. For any civilization witnessing this, the sight would inspire awe, wonder, maybe fear, certainly a profound sense of being part of something much larger than themselves. It would be a reminder, visible every night, that the universe is dynamic and changing, that even galaxies are not permanent, and that on cosmic timescales, everything is in flux. And it would be beautiful, chaotic, turbulent, unprecedented, but undeniably beautiful. The sky during first passage would be unlike anything that's been seen before in the history of either galaxy, and it would be a sight that astronomers, artists, and anyone who simply looks up at night would remember and cherish. After the drama and chaos of the first passage, something that might seem surprising happens. The galaxies separate. They don't immediately stick together and merge. Instead, they pull apart, moving away from each other, driven by the momentum they had when they collided. This might seem counterintuitive. If gravity is pulling them together, why would they separate after colliding? The answer has to do with orbital mechanics and the conservation of energy and angular momentum. Think about a comet approaching the sun. As it gets closer, it speeds up. Pulled by the sun's gravity, it swings around the sun in a tight arc and then flies back out into the solar system. It doesn't fall into the sun because it has too much speed and angular momentum. It has to swing back out. The same principle applies to galaxies. The Milky Way and Andromeda have been approaching each other for billions of years, accelerating as they get closer. By the time they reach the point of closest approach during the first passage, they're moving at tremendous velocities relative to each other, possibly several hundred kilometers per second or more. That momentum carries them through the collision and out the other side. They interpenetrate, their stars mixing together, their gas clouds colliding. But they don't lose enough energy during the first pass to become bound into a single merged system. They have too much kinetic energy, so they separate again, pulled apart by their own momentum. Imagine throwing a ball straight up in the air. Gravity pulls it down, slowing it as it rises. Eventually, it stops rising and starts falling back down. But for a moment, it's moving away from you, even though gravity is pulling it toward you the whole time. That's what's happening with the galaxies. After the first pass, how far apart do they get? That depends on the details of the collision, how fast they were moving, how they were oriented, how much energy was dissipated during the collision. Computer simulations suggest they might separate by several 100,000 light-years, possibly even 1,000,000 light-years or more. That might sound like they're moving far apart, but remember, they approached from 2.5 million light-years away. So even after separating, they're closer together than they were before the first collision. And they're still gravitationally bound to each other. They will come back together. How long does this separation last? Again, it depends on the details, but typically, hundreds of millions of years. The galaxies swing apart, gradually slow down as gravity works against their motion, eventually come to a stop, and then begin falling back together for the second passage. During this separation phase, both galaxies are recovering from the first pass, though recovering might not be the right word. The damage has been done. The spiral structure has been disrupted. Tidal tails have been formed. Star formation has been triggered. These effects don't reverse during the separation phase. If anything, they continue to evolve. The tidal tails, for instance, continue to stretch and elongate. Stars in the tails are still moving outward, following the trajectories they were kicked onto during the first pass. The tails grow longer, eventually reaching distances of hundreds of thousands of light-years from the main bodies of the galaxies. The star formation triggered by the collision also continues. Gas clouds that were compressed during the first pass are still collapsing, forming new stars. The massive stars that formed during the collision are evolving rapidly. Some are already exploding as supernovas, injecting energy back into the interstellar medium. From a visual perspective, during the separation phase, the two galactic cores would be moving apart in the sky. If you're observing from within one of the galaxies, you'd see the other galaxies slowly receding, getting smaller and fainter over millions of years. But it wouldn't get small or faint enough to disappear. Remember, after the separation, the galaxies are still much closer than they were before the first collision. Andromeda would still be a prominent feature in the sky, larger and brighter than it was billions of years before the collision began. The tidal tails would remain visible as well, long streams of stars connecting the two galaxies even as they separate. These tails are evidence of the gravitational interaction. Bridges of stars linking the two galaxies even across the vast distances separating them. During the separation phase, astronomers would be able to measure the motion of both galaxies precisely. They'd be able to calculate when the galaxies would swing back together for the second pass. They'd be able to refine their models of the merger, comparing observations to simulations and adjusting their predictions. For any civilizations present, this might be a time of preparation. The first pass has shown what the collision looks like, what effects it has. There's been time to observe, to measure, to understand. Now, with the second pass coming, there would be an opportunity to prepare, to move populations if necessary, to build infrastructure that can withstand the ongoing disruption. But there's also a sense of inevitability. The galaxies are going to come back together. Nothing can stop it. The gravitational dance that began billions of years ago when the galaxies first started approaching will continue through multiple passages until finally, after losing enough energy, the galaxies settle into a single merged structure. This separation phase is also when some stars can be permanently lost from the system. A small fraction of stars, those that were kicked particularly hard during the first pass, might reach escape velocity. These stars are ejected from the merging system entirely, flung out into intergalactic space. These ejected stars become what are called intergalactic stars or hypervelocity stars. They're no longer part of any galaxy. They're wandering through the void between galaxies, traveling at high speeds, destined to spend billions of years in isolation unless they happen to encounter another galaxy far in the future. If the Sun were one of these ejected stars, which is unlikely but possible, then during the separation phase, we'd see both the Milky Way and Andromeda receding from us. Over millions of years, they'd get smaller and fainter, eventually becoming just bright patches in the distance. We'd be alone in intergalactic space, traveling away from our place of origin, with no nearby galaxies and a very dark night sky. But most stars remain bound to the system. Most stars, including probably the Sun, will go through all the passages, experiencing each collision, having their orbits scrambled repeatedly, until finally ending up as part of the merged galaxy. The separation phase is temporary, a brief respite between passages. It's a time when the galaxies catch their breath, so to speak, before plunging back together for another round of gravitational chaos. And during the separation, as the galaxies slow down and begin falling back together, there's a building sense of anticipation. The second pass is coming. It will be similar to the first in many ways, but also different because the galaxies have already been disrupted. They're no longer intact spiral galaxies. They're partially merged, already chaotic structures that are about to be disrupted even further. The second pass will be more violent than the first in some ways because the galaxies are more vulnerable. Their structure has already been weakened. The tidal forces will pull on already disrupted regions, stretching them further, creating even more chaos. But the second pass will also be slower than the first. The galaxies have lost some energy during the first collision, mostly through the process of stars and gas being flung into new orbits. So when they come back together, they're not moving quite as fast. They spend more time close together, allowing gravitational forces more time to act. This pattern will repeat with each passage. The galaxies collide, separate, swing back together. Each collision is slower than the last. Each separation is shorter. Gradually, over billions of years, the galaxies spiral together, losing energy, until finally they merge completely. The merger of the Milky Way and Andromeda isn't a one-time event. It's a process that unfolds over multiple passages, with the galaxies colliding, separating, and colliding again, each time coming closer together, each time losing more energy, until finally they settle into a single, merged galaxy. How many passages will there be? Computer simulations suggest somewhere between 3 and 5 major passages, possibly more depending on the exact geometry of the collision and how much energy is lost in each encounter. Each passage takes tens of millions of years, and the separation between passages lasts hundreds of millions of years, so the entire process of multiple passages stretches across roughly 2 billion years. That's an enormous span of time. For perspective, 2 billion years ago on Earth, life consisted only of single-celled organisms. There were no plants, no animals, no complex multicellular life of any kind. Everything that's happened in the evolution of complex life on Earth has occurred in less time than it will take the Milky Way and Andromeda to fully merge. Why do the galaxies need multiple passages? Why don't they just merge on the first collision? The answer has to do with energy and how galaxies lose it. When the galaxies first collide, they have a lot of kinetic energy, the energy of motion. They're moving fast, and that kinetic energy has to go somewhere before they can settle down into a merged state. Energy can't just disappear. That would violate conservation of energy, so it has to be transferred somewhere else. One way energy gets transferred is through stars being flung into new orbits. When a star gets kicked by gravitational interactions during the collision, it ends up moving faster than before. That extra speed is energy that came from the orbital motion of the two galaxies. The galaxies lose kinetic energy, and the star gains it. Another way energy is lost is through what's called dynamical friction. This is a subtle effect, but it's important. When a massive object, like the dense core of a galaxy, moves through a sea of less massive objects, like the stars in the outer parts of the galaxy, it gravitationally attracts those objects. The objects accelerate toward the massive object, and by Newton's third law, the massive object is slowed down by the gravitational interaction. It's similar to friction, but it's happening through gravity rather than through physical contact. The dense cores of both galaxies experience dynamical friction as they move through the more diffuse outer regions, and this gradually saps their orbital energy. Gas collisions also dissipate energy. When two clouds of gas crash together, the kinetic energy of their motion gets converted into heat. The gas heats up, and then it radiates that heat away as light. This radiation carries energy away from the system, energy that's ultimately lost into space. Unlike stars, which don't collide and don't radiate, gas can lose energy efficiently, and this helps the galaxies shed orbital energy. But these energy loss mechanisms are gradual. During the first pass, only a fraction of the orbital energy is lost. The galaxies still have enough energy to separate again. It's only after multiple passages, after enough energy has been dissipated, that the galaxies finally lose the ability to separate and remain bound together. Each passage is similar, but also different from the previous one. The basic pattern is the same. The galaxies approach, interpenetrate, tidal forces pull on both, gas clouds collide, star formation is triggered, and then they separate again. But the galaxies are changing with each passage. The spiral structure, already disrupted after the first pass, becomes completely unrecognizable after the second or third. The tidal tails grow longer and more complex, with stars from multiple passages contributing to them. The stellar orbits become increasingly random and chaotic. By the third or fourth pass, the galaxies don't even look like galaxies anymore in the traditional sense. They look like two colliding blobs, irregular and amorphous, with long tails streaming away and complex structures threading through the regions where they overlap. The star formation rate fluctuates with each passage. During each collision, gas clouds are compressed, and star formation spikes. During the separation phases, star formation drops back down to lower levels. But each spike of star formation adds more young stars to the system, more massive stars that will eventually explode as supernovas. The cumulative effect of these starburst episodes is significant. Over the course of the merger, a substantial fraction of the galaxy's gas is converted into stars. Some estimates suggest that as much as 10 to 20% of the total gas might be turned into stars during the merger, a huge amount compared to the normal star formation rates in isolated spiral galaxies. The stellar populations get thoroughly mixed during the multiple passages. Stars that originated in the Milky Way and stars that originated in Andromeda pass through each other again and again. By the final passage, they're so intermingled that you couldn't tell which galaxy any individual star came from. They're all just part of the merged system. This mixing also applies to stellar populations of different ages. The Milky Way and Andromeda each have a history of star formation going back 13 billion years. They each contain old stars, middle-aged stars, and young stars. During the merger, all these populations get mixed together, creating a galaxy with a complex and varied stellar population. The dark matter halos are also merging during these passages. Remember, the dark matter doesn't collide like gas does. It just interpenetrates, with particles from each halo passing through each other. But over multiple passages, the dark matter from both halos gets completely mixed together, forming a single merged halo that encompasses the entire system. This merged dark matter halo is what provides the gravitational framework for the final merged galaxy. The visible matter, the stars and gas, settle into orbits within this dark matter halo, held together by its gravity. The supermassive black holes at the centers of both galaxies are getting closer with each passage. During the first pass, they're separated by perhaps tens of thousands of light years as the galactic cores pass by each other. During subsequent passes, they get closer, maybe just thousands of light years apart. But they don't merge yet. Even though they're getting closer, they're still too far apart and moving too fast to directly interact. It's only after the galaxies have lost enough energy and the cores have finally merged that the black holes end up close enough to form a binary system and eventually merge. We'll talk more about that later. Each passage also creates opportunities for different regions of the galaxies to interact. During the first pass, certain regions might collide head-on, while others barely interact. During the second pass, with the galaxies oriented differently, different regions collide. This creates a complex pattern of interactions over time, with some regions experiencing multiple strong collisions and others remaining relatively undisturbed. For any observers watching the multiple passages, each one would be slightly different. The first pass might come from one direction, with Andromeda approaching from a particular angle. The second pass might come from a different direction as the galaxies swing back together along a different trajectory. The sky would change with each passage, familiar features disappearing and new structures appearing. The multiple passages also give any civilizations time to adapt. Between passages, during the separation phases, there are hundreds of millions of years to recover, to rebuild, to move populations to safer locations if necessary. The merger isn't a single catastrophic event. It's a series of events spread over billions of years, giving intelligent life, if any exists, time to respond and adapt. After each passage, the separation distance gets shorter and the separation time gets briefer. The galaxies are losing energy, spiraling together. Eventually, after the third, fourth, or fifth passage, they no longer have enough energy to separate significantly. They remain close together, their cores embedded in a common envelope of stars and dark matter, spiraling slowly towards each other until they finally merge completely. This final merger of the cores marks the end of the multiple passage phase and the beginning of the relaxation phase, where the merged galaxy settles into a stable configuration. But that's still far in the future at this point. For now, the galaxies are locked in their gravitational dance, colliding and separating, each passage bringing them closer to their final destiny as a single merged galaxy. One of the most profound transformations during the merger is the complete destruction of the beautiful spiral arms that characterize both the Milky Way and Andromeda. Spiral structure is one of the defining features of these galaxies, and its loss marks the transformation from spiral galaxies to something completely different. Let's start by understanding what maintains spiral structure in the first place. Spiral galaxies aren't like pinwheels where the arms are rigid structures that rotate as a unit. If they were, the arms would wind up tighter and tighter over time as the galaxy rotates, and within a few rotations, they'd be completely wound up, which clearly hasn't happened. Instead, spiral arms are density waves. They're regions where stars and gas are temporarily more concentrated. As stars orbit around the galactic center, they move into and out of these density waves. When stars enter a spiral arm, they slow down slightly, like cars entering a traffic jam. This causes them to spend more time in the arm, which maintains the higher density. When they leave the arm, they speed up again. The spiral arms persist because the density wave itself rotates at a different speed than the stars. The wave pattern rotates slowly, while individual stars orbit faster. This allows the spiral structure to remain stable over billions of years, even though stars are constantly moving through it. Gas responds even more dramatically to spiral arms. When gas enters a spiral arm, it gets compressed by the higher density. This compression can trigger star formation, which is why spiral arms appear bright and blue. They're full of young, hot stars that formed recently. This entire mechanism depends on the organized, coherent rotation of the galactic disk. All the stars are moving in roughly the same direction, in roughly the same plane, in roughly circular orbits. This organized motion creates the conditions for density waves to form and persist. But during a galaxy merger, all of that organization gets destroyed. The gravitational perturbations from the collision kick stars into new orbits. Some stars get pulled into more elliptical orbits, some get kicked out of the plane of the disk, some get accelerated, others decelerated. The result is that the coherent, organized rotation breaks down into chaotic, random motion. Once the organized rotation is gone, density waves can't persist. The spiral arms begin to fade. The structure that maintained them no longer exists. What you're left with is a more uniform distribution of stars with no particular pattern or organization. This process begins during the first passage, but takes multiple passages to complete. After the first pass, the spiral structure is badly disrupted, but still vaguely recognizable. You can see remnants of the arms, distorted and stretched, but still there. After the second or third pass, the spiral structure is gone entirely. The galaxies no longer look like spirals. They look like irregular, amorphous collections of stars, with no clear pattern or organization. And by the time the merger is complete, the final galaxy is an elliptical, a roughly spherical or ellipsoidal distribution of stars, with no disk structure at all. The transformation from spiral to elliptical is complete. This transformation is actually one of the ways astronomers know that elliptical galaxies form from mergers. When you observe elliptical galaxies, you see certain features that are consistent with a merger origin. For instance, elliptical galaxies often have shells and ripples in their stellar distributions, features that simulations show are created during mergers. Elliptical galaxies also have stellar populations that are thoroughly mixed, with stars moving in random directions rather than organized rotation. This is exactly what you'd expect from a merger, where the original organized motion was scrambled. The loss of spiral structure has other consequences too. Spiral arms are where most star formation happens in spiral galaxies. The compression of gas as it moves through spiral arms triggers star formation, creating the bright blue regions we see in the arms. Without spiral arms, this mechanism for triggering star formation is gone. Elliptical galaxies do still form some stars, but at much lower rates than spiral galaxies. They're dominated by old red stars rather than young blue stars. This is partly because elliptical galaxies have used up or lost most of their gas during the merger. Gas collisions during the merger convert a lot of gas into stars. Supernova explosions and stellar winds heat the remaining gas, possibly driving it out of the galaxy entirely. And without much gas left, there's not much raw material for forming new stars. So the merger doesn't just destroy the spiral structure, it also shuts down star formation, transforming both galaxies from actively star-forming spirals to passively evolving ellipticals. Another consequence of losing spiral structure is that the disk itself gets puffed up. In a spiral galaxy, the disk is thin, with most stars confined to a relatively narrow plane. In an elliptical galaxy, stars are distributed throughout a much larger volume, creating a more three-dimensional structure. This happens because stars get kicked into orbits that are tilted relative to the original plane of the disk. Some stars end up on orbits that take them high above and below the original disk plane. The result is that what was once a flat disk becomes a more spherical or ellipsoidal structure. The final shape of the merged galaxy depends on the details of the merger. Some mergers produce galaxies that are nearly spherical. Others produce elongated ellipticals that are more rugby ball-shaped than spherical. The shape depends on factors like the mass ratio of the two galaxies, their relative orientations during the collision, and how much rotation the merged galaxy retains. For the Milky Way Andromeda merger, simulations suggest the final galaxy will be a fairly round elliptical, possibly with some residual rotation. It will be larger than either of the original galaxies, containing all the stars from both, but distributed over a larger volume. The loss of spiral structure is also aesthetically significant. Spiral galaxies are beautiful, with their elegant arms and organized structure. Elliptical galaxies are less visually interesting, just smooth, featureless distributions of stars. The merger trades beauty for chaos, though of course that's a human aesthetic judgment. The universe doesn't care what galaxies look like. But for any civilizations observing the merger, the loss of spiral structure would be noticeable and perhaps melancholy. The familiar spiral pattern that's been a feature of the galaxy for billions of years would gradually fade away, replaced by something less structured and less beautiful. There's also a practical consequence. In a spiral galaxy, the spiral arms serve as landmarks. You can use them to navigate, to orient yourself, to describe locations. We're in the Orion Spur, between two major spiral arms, is a meaningful description in the Milky Way today. In an elliptical galaxy, there are no such landmarks. The distribution of stars is more uniform, with fewer distinctive features. Navigation would have to rely on other methods, perhaps mapping the positions of particular stars or star clusters, rather than using large-scale structures. The death of spiral structure is one of the most visible signs that the merger is progressing. It's a transformation that happens gradually over billions of years, but once it's complete, there's no going back. The merged galaxy is fundamentally different from its spiral progenitors, and that difference is immediately visible in its structure. Throughout the merger, but especially during the peak phases when the galaxies are actively colliding, there's an intense period of star formation called a starburst. This is when the merger creates ideal conditions for forming stars at rates far higher than normal, and it's one of the most dramatic and consequential phases of the entire event. Let's start with normal star formation to understand why starbursts are special. In an isolated spiral galaxy like the Milky Way today, star formation happens at a relatively steady rate of a few solar masses per year. That means, each year, the galaxy converts about 2 or 3 times the mass of the Sun worth of gas into new stars. This rate is sustained by the gradual compression of gas in spiral arms, and by supernova explosions that trigger the collapse of nearby gas clouds. It's a self-regulating process. Star formation creates massive stars, which explode as supernovas, which triggers more star formation, but also heats and disperses gas which limits star formation. During a starburst, all of this balance gets thrown out. The star formation rate can increase by factors of 10, 100, or even 1,000. Instead of forming a few solar masses of stars per year, the galaxy might form hundreds or thousands. This intense star formation can't be sustained for long, typically just a few tens of millions of years. But while it lasts, it transforms the galaxy. What triggers a starburst during a galaxy merger? The answer is gas collisions. When two galaxies collide, their gas clouds also collide. And when gas clouds collide at high velocities, several things happen. First, the collision compresses the gas. The density increases dramatically in the collision zone. Gas that was spread out over large volumes gets squeezed into much smaller regions. Second, the collision creates shock waves, regions where gas transitions abruptly from one velocity to another. Shock waves can trigger additional compression, further increasing the density. Third, the collision can strip gas from its original location and funnel it toward the centers of the galaxies. Tidal forces and the chaotic gravitational environment of the merger can push gas inward, creating dense concentrations of gas near the galactic cores. All of these processes create conditions that are ideal for star formation. The gas is dense, it's relatively cold because it can radiate away heat through emission lines, and there are trigger mechanisms everywhere: shocks, compressions, turbulence. The result is that gas clouds throughout both galaxies start collapsing into stars at rates far higher than normal. And because the conditions favor the formation of massive stars, which are the most luminous, the result is a galaxy that suddenly becomes much brighter, especially in blue and ultraviolet light. These massive stars don't live long. A star weighing 20 solar masses lives only about 10 million years. A star weighing 50 solar masses lives just a few million years, so the massive stars born during the starburst will die very quickly by astronomical standards. And when they die, they explode as supernovas. Each supernova releases as much energy as the Sun will emit over its entire 10 billion-year lifetime, all in a few seconds. This energy heats the surrounding gas, creating bubbles of hot plasma. It also injects heavy elements into the interstellar medium, enriching the gas with elements like carbon, oxygen, silicon, and iron. The rate of supernova explosions during a starburst can be hundreds of times higher than normal. In the Milky Way today, we get about 1 or 2 supernovas per century. During the starburst phase of the merger, we might see hundreds of supernovas per century, possibly even more. From an observational perspective, this would be spectacular. The night sky would be filled with bright blue star-forming regions, each one glowing with the light of thousands or millions of newly formed stars. And supernovas would be going off constantly, bright points of light that appear, brighten, and fade over the course of weeks or months. If you're in a civilization with telescopes, you'd be able to see these star-forming regions in incredible detail. You'd see the dense molecular clouds where stars are forming, the glowing nebulae surrounding young star clusters, the supernova remnants expanding outward from exploded stars. Each star-forming region would be a laboratory for studying stellar birth and evolution. You'd be able to watch stars form in real time, see how they interact with their environment, observe how they affect the gas around them. But the starburst also has downsides, particularly for any life that might be present. The intense ultraviolet radiation from massive stars can strip away planetary atmospheres. Supernova explosions can bathe planets in X-rays and gamma rays, potentially causing extinction events. If you're on a planet in or near a starburst region, the environment becomes much more hazardous. The radiation levels are higher, the rate of nearby supernovas is higher, the interstellar medium is more turbulent and chaotic. On the other hand, if you're far from the starburst regions, in a quiet part of the galaxy, you might be largely unaffected. The starburst happens in specific locations where gas is being compressed. Vast regions of both galaxies might experience little or no increase in star formation. The starburst also consumes a lot of gas. Remember, star formation converts gas into stars. During the starburst, a significant fraction of the galaxy's gas reservoirs gets turned into stars within just a few tens of millions of years. Once the gas is used up, star formation drops dramatically. The starburst ends, and the galaxy is left with a population of newly formed stars, but much less gas for future star formation. This is one reason elliptical galaxies have low star formation rates. They've used up most of their gas, either by converting it to stars during the merger, or by heating it and driving it out of the galaxy through supernova-driven winds. The starburst also enriches the galaxy with heavy elements. Every massive star that explodes as a supernova adds elements heavier than helium to the interstellar medium. Over millions of years, as hundreds or thousands of supernovas go off, the amount of heavy elements in the galaxy increases noticeably. This enriched gas will eventually be incorporated into new stars and planets. Any planetary systems that form after the starburst will have access to a richer mix of elements than systems that formed before. Rocky planets might be larger or more numerous. The chemistry of life might be different if there are more heavy elements available. The starburst phase of the merger is also when the most luminous stars in the galaxy's history are born. Stars weighing 100 solar masses or more, the most massive stars possible, are rare in normal circumstances. But during a starburst, conditions might allow these extreme objects to form. These hypermassive stars are incredibly luminous, potentially millions of times brighter than the Sun. They're also incredibly short-lived, burning through their fuel in just 1 million years or so before collapsing into black holes. If any of these hypermassive stars form during the merger, they would be visible across the entire galaxy. Brilliant beacons of light, marking the locations of the most intense star formation. The starburst phase lasts for a relatively short time, maybe 50 to 100 million years during the peak of the merger, but its effects last much longer. The stars formed during the starburst will continue to exist for billions of years, depending on their masses. The heavy elements injected into the interstellar medium will affect star and planet formation for the rest of the galaxy's life. And the disruption to the gas, the heating and dispersal caused by all those supernovas, will affect the galaxy's structure for billions of years. In many ways, the starburst is the climax of the merger, the moment when the collision's effects are most dramatic and most visible. It's a period of intense creation, intense destruction, and intense transformation, all happening at once. At the very centers of both the Milky Way and Andromeda sit supermassive black holes, objects so massive and so dense that not even light can escape their gravity. And during the merger, these two monsters are on a collision course that will eventually bring them together in one of the most energetic events in the universe. Let's start with a reminder of what we're dealing with. The Milky Way's black hole, Sagittarius A, pronounced Sagittarius A star, weighs about 4 million times what the Sun weighs. That's 4 million solar masses, a staggering amount of mass compressed into a region smaller than the orbit of Mercury. We can't see the black hole directly because it's black. No light escapes, but we can see stars orbiting around it. By tracking these stars over years and decades, measuring their positions and velocities with incredible precision, astronomers can calculate the mass of the invisible object they're orbiting. The answer is unambiguous. There's a 4 million solar mass black hole at the exact center of our galaxy. Andromeda's black hole is much larger. Estimates put it at somewhere between 100 and 200 million solar masses, at least 25 times more massive than Sagittarius A, possibly 50 times more massive. This difference in size will matter when the black holes eventually merge. Both black holes are currently sitting at the centers of their respective galaxies, surrounded by millions of stars packed into the dense central bulges. As the galaxies approach each other and begin to merge, these central regions are coming together as well. During the first few passages, the black holes are still far apart. When the galactic cores pass by each other, the black holes might be separated by tens of thousands of light years. At these distances, they don't directly interact. They're each sitting at the center of their own core, surrounded by their own population of stars. But with each passage, the cores get closer. The galaxies are losing energy, spiraling together. And as the cores approach, so do the black holes. Eventually, after multiple passages, the cores merge. Instead of two separate dense regions passing by each other, they settle into a single merged core at the center of the new galaxy. And somewhere within that merged core, the two black holes are orbiting each other. This is when things get interesting. Two supermassive black holes, one weighing 4 million solar masses and the other weighing perhaps 100 million solar masses, are now gravitationally bound to each other. They're orbiting their common center of mass, which, given the mass difference, is much closer to the larger black hole. The process of bringing the black holes together is driven by dynamical friction, the same mechanism that brings the galactic cores together. As each black hole moves through the sea of stars in the merged core, it gravitationally attracts those stars. The stars accelerate toward the black hole, and by Newton's third law, the black hole is slowed down. This drag force gradually saps the orbital energy of the two black holes. They're still orbiting each other, but the orbit is slowly shrinking, bringing them closer and closer together. How long does this take? That depends on the density of stars in the merged core and the initial separation of the black holes. Estimates vary, but it could take hundreds of millions of years, possibly even a billion years or more, for the black holes to spiral from their initial separation of thousands of light years down to a separation where they can actually merge. As they get closer, the orbital period gets shorter. Initially, they might orbit each other once every few million years. As they spiral inward, the period drops to hundreds of thousands of years, then tens of thousands, then thousands, then hundreds. Eventually, when they're separated by just a few light years or less, something else starts to matter. Gravitational waves. Gravitational waves are ripples in space-time itself, created by accelerating masses. Any two objects orbiting each other emit gravitational waves, but the effect is only significant when the masses are large and the orbital velocities are high. Two supermassive black holes orbiting each other closely emit copious amounts of gravitational waves, and these waves carry energy away from the system. As energy is radiated away in gravitational waves, the orbit shrinks even faster. This creates a runaway effect. The closer the black holes get, the more gravitational waves they emit. The more gravitational waves they emit, the faster they lose energy. The faster they lose energy, the closer they get. The process accelerates exponentially. When the black holes are separated by just a few light hours or light days, the orbital period drops to hours, then minutes, then seconds. They're orbiting each other at a significant fraction of the speed of light, emitting gravitational waves at a prodigious rate. And then finally, they merge. The two black holes combine into a single, larger black hole weighing about 104 million solar masses, 4 million plus 100 million. Though a small amount of mass gets converted directly into gravitational waves during the merger itself happens incredibly quickly, over just a fraction of a second. Two black holes orbiting at nearly the speed of light suddenly combine. The event horizon, the boundary beyond which nothing can escape, morphs and ripples as the two black holes coalesce. Within milliseconds, it settles into a smooth, spherical shape characteristic of a single black hole. The amount of energy released during this merger is staggering. Some estimates suggest that as much as 5% of the combined mass of the black holes could be converted directly into energy in the form of gravitational waves. That's equivalent to converting several million solar masses into pure energy in a fraction of a second. To put that in perspective, The sun has been shining for 4.6 billion years, radiating energy constantly, and over its entire lifetime, it will convert less than 0.1% of its mass into energy. The black hole merger releases more energy in a fraction of a second than the sun will emit over its entire 10 billion year lifespan. But here's the key point. This energy is emitted as gravitational waves, not as light. Gravitational waves don't interact with matter the way light does. They pass right through everything. Planets, stars, even you barely noticed. So, from a visual perspective, the black hole merger is anticlimactic. There's no flash of light, no explosion, no visible display. If you're watching the galactic center when the black holes merge, you won't see anything unusual. The black hole merger happens in complete silence and darkness as far as electromagnetic radiation is concerned. But if you have a gravitational wave detector, you'd observe one of the most powerful events in the universe. The gravitational wave signal from merging supermassive black holes is incredibly strong, visible across vast distances. Future space-based gravitational wave detectors, like the planned LISA mission, are designed specifically to detect signals from merging supermassive black holes. When the Milky Way and Andromeda merge, the gravitational waves from the black hole merger will sweep across the universe. Any civilization in the local group or beyond, with the right technology, will be able to observe it. The merger also has another effect, the recoil kick. When two black holes merge, if they're spinning in particular ways, the asymmetric emission of gravitational waves can give the merged black hole a kick, a recoil velocity. This kick can be quite substantial, potentially hundreds or even thousands of kilometers per second. A black hole kicked at these velocities would take millions of years to settle back down at the center of the galaxy. During this time, the black hole would be wandering through the galaxy, a supermassive black hole moving at high speed through the stellar population. Any star that got too close would be captured or destroyed, adding to the black hole's mass. Eventually, dynamical friction would slow the black hole down, and it would sink back to the galactic center where it belongs. But for a while, the merged galaxy would have a wandering supermassive black hole, an unusual and potentially dangerous object. The final merged black hole, weighing about 104 million solar masses, will sit at the center of the new elliptical galaxy. It will be the gravitational anchor of the galaxy, with all the stars orbiting around it. Over billions of years, it will occasionally accrete gas or capture a star, growing very slowly, but for the most part, it will just sit there, a dark, massive presence at the heart of the galaxy, a permanent reminder of the merger that created it.